1951. The mission was to map the nation with the ultimate goal of understanding the country's mineral potential and geological superlatives. As the survey expanded, so did its discoveries. These resources fueled India's industrial growth. When the chains of colonial rules broke, a new purpose emerged. The new India sought its own treasures. From the coal fields of Ranganj to the copper deposits in Khetri, from iron ore of Singhbhum to shimmering gold of Kolar, each mission was a testament of dedication. GSI expanded both in form, structure, and capacity. What began as small-scale research expeditions evolved into a series of groundbreaking missions that have shaped our understanding of the world and beyond. Today, the Geological Survey of India is a premier geological organization providing support to India's growth. Established in 1965, the Marine and Coastal Survey Division of GSI has been the nation's silent sentinel along India's coasts, mapping uncharted waters, revealing hidden treasures, and safeguarding marine ecosystems. Today, the division stands as the backbone of India's blue economy. In the decades that followed, GSI transformed with modern tools of remote sensing, geophysics, and modern surface exploration tools in land, air, as well as ocean areas of the subcontinent. Beyond India, GSI's research extended to the icy frontiers of Antarctica, contributing to the global climate and geological studies. With the turn of the century, GSI harnessed the power of technology. No longer just about maps and rock hammers, it became a hub of innovation, using drones, AI, and satellite data to explore and protect India's geological treasures. Through the National Geological Data Repository, GSI is creating a comprehensive database of India's geological history, helping predict mineral resources, analyze geological samples, and
Good morning, everyone.
and
All are requested to kindly please settle down. We are going to start today's session in next 5 minutes. We'll be starting sharp at 10 a.m. So please settle down, relax yourself. You'll be having some engaged. We'll be having some sessions today which will be totally added some good amount of values to our knowledge and understanding. So settle down first. We are going to start in next 5 minutes. Hello. Good morning, distinguished guests, delegates, and participants. Welcome. Welcome to day 2 of Next Gen Geophysics 2025, Unlocking Earth's Hidden Treasures, hosted by Geological Survey of India, Ministry of Mines, at GSI-TI Hyderabad, and this event celebrates 175th years of GSI's legacy in geoscience and mineral exploration. I am Abhijit Nath, and joining me is my colleague, Ms. Suman Paul. We are honored to guide you through another exciting day of knowledge sharing and innovation.
With global demand surging for critical and strategic minerals, geophysics plays a pivotal role in supporting initiatives like Atmanirbhar Bharat and the National Mineral Policy and the National Critical Mineral Mission. We are proud to have Steiger Geoscience and Engineering Private Limited as our event partner. We also acknowledge the support of our platinum sponsors, Critical Mineral Trackers, Data Code, Mining Tech Consultancy Services, our gold sponsors, Mineral Exploration Corporation Limited, Altera Solutions, Geomarine Solutions Private Limited, Hind Metal Exploration Services Private Limited, Summit Spectrum Private Limited, and our silver sponsors, Maheshwari Mining Private Limited, United Exploration India Private Limited, Geo Expo Private Limited, and Spry Technocon Private Limited.
Today's highlights include cutting-edge session on airborne electromagnetic, AI-driven modeling, 3D magnetotelluric, and integrated geophysics. Expert talks on multi-parameter survey and mineral prospectivity mapping, and a high-level panel discussion on the topic of India's role in global critical mineral security.
We look forward to a day of insight, collaboration, and bold ideas as we continue unlocking the Earth's hidden treasures together.
Ladies and gentlemen, to begin today's proceedings, it is our honor to invite the session chair for the forenoon session of today's event, Sri D.V. Ganveer, Additional Director General, Head of Department, Central Region Geological Survey of India, and National Mission Head 2, Geological Survey of India. With over 30 years of exemplary service, Sir has led major initiatives in geological mapping, mineral exploration, engineering geology, and heritage conservation. From exploring gold in Maharashtra to overseeing seismic hazard projects in the Northeast and critical mineral development nationwide, his contributions span both technical excellence and strategic leadership.
Currently, he directs more than 449 national exploration projects under National Mission 2, supports state mineral auctions, and champions innovation through initiatives like digital core libraries. His dedication is reflected in exceptional project delivery and resource management. Please join me in welcoming Shri D.V. Ganveer sir to chair this morning session. Sir, please.
Ladies and gentlemen, it's a great honor to welcome our first distinguished speaker for the day, Dr. Alexander Pikhotko, Vice President and Chief Geophysicist at Expert Geophysics. With nearly 2 decades of global experience in airborne geophysics, Dr. Prikhotko is a recognized expert in airborne electromagnetics. His groundbreaking work has supported mineral exploration across continents and earned him the Burlow Medal from Canadian Institute of Mining in year 2019.
Today, he'll speak on transforming mineral exploration with a natural total field airborne electromagnetic system, a deep dive into how emerging airborne technologies are redefining exploration efficiency and depth capability. Please join me in welcoming Dr. Alexander Prikhotko virtually.
Alexander, your slides is visible, and let me check your audio. Can you speak?
Yes, hello. Hello, everybody.
You're perfectly audible as well.
So you can start.
Thank you so much. So first of all, many thanks to organizer for inviting me to make this presentation at the conference. So I will introduce you to the airborne electromagnetic technology based on using natural fields with the support of several real examples. So I will just remind you that all airborne electromagnetic methods are inductive methods, which are different, first of all, in the primary field sources. As a consequence, the main difference between the methods are in the depth of investigation. On the left side of the slide, you can see the average depth of investigation, each of them VLF, frequency domain, time domain, and natural field methods. In resistive, which is blue squares here, and conductive red environments. So as you can see, the natural field group of methods are most deepest in depth of investigation, greatest in depth of investigation, even in conductive environment. Another important output of the methods is the resistivity detectability range. As you can see, for example, the time domain method, which is here, time domain method, only partly covers possible resistivities of rocks and minerals. But in contrast, frequency domain and natural field systems are covering the full range of possible resistivities. So mobile MT technique, in contrast to other airborne AM systems, it's called passive technology, uses natural electromagnetic field to investigate the electrical conductivity of the subsurface. The passive systems don't use any artificially driven generator or transmitter, which first of all creates noise, and secondly is very limited by energy in airborne modifications. Lightning events and thunderstorm activity worldwide in global scale cause natural variations in the Earth's magnetic field, including electric or telluric currents. The natural phenomenon creates strong EM source signals over the audio frequency band which are measured. Simplifying, the Earth is constantly charged with lightning, and the transmitting field is always present underground. We don't need local thunderstorm. This process is going globally over the Earth. So we have, in mobile MT technology, we have up to 30 windows, frequency windows, from around 26 Hertz to 21 kilohertz. Frequencies means depth of investigation. Lowest frequencies are responsible for deepest penetration, and high frequencies reflect near surface geology. The system consists of two main parts. It's a moving sensor under the helicopter or under a drone, three-component coils which record variations of magnetic field, and base station, stationary base station on the ground, which measure the variations of electric field. So in the results, we have 3 channels of variation, time series data from magnetic sensor, magnetic variation sensor, and actually it's 2 pairs of electrical components, orthogonal electrical components. Basically, the data processing is very close to ground magnetotellurics. In the results of the data, of the time series data processing, we calculate apparent conductivities corresponding to different frequencies. This is just real examples of apparent conductivity data along a survey line. So in the nutshell, the three-component measurement of magnetic field variations provides us sensitivity to any direction sorry, of geoelectrical boundaries, from horizontal to vertical. The frequency measurement from 26 Hz to 21 kHz provide us sensitivity to both near surface and deep geological structures. And the frequency range is divided up to 30 windows. Depending on signal, usually we invert data from 15 to 25 channels. This provides high in-depth resolution and wide range of data selection. So depth of investigation of the method can be estimated based on skin depth, depending on frequency and Hall space resistivity. Just theoretical estimation on uniform Hall space resistivity. You can see even in more or less conductive environment, like 100 ohm meters, we can reach more than 1 kilometer depth of investigation. So here's an example of depth investigation estimation based on inversion of the real data based on Jacobian matrix. It reflects sensitivity of data. And this is a very deep conductive layer, more than 1.5 kilometer depth, up to 3 kilometers depth in comparatively resistive environment, which is depth of investigation is estimated based on the sensitivity during the inversions. So here it's example. We usually invert the data from apparent conductivity frequency into resistivity depth images, like here presented in this slide. We use Marie2DM software, and our input data apparent conductivity for different frequencies. And this is a resistivity depth section, resistivity depth slices, sections into 3D, and resistivity voxel. So here's an example of comparison, direct comparison with time domain data. So along the line, both examples are from Ontario in Canada. On the left side, you can see the several conductors which are near surface, comparatively near surface, and we can see time domain anomalies pretty well, but in case of highly conductive targets, depth of investigation becomes, for time domain method, becomes very limited because conductors work like a shield, electromagnetic shield, and the penetration of the transmitting field is problematic in these conditions. So the same line was flown with mobile MT system, and we can get the full picture, geologically meaningful picture. We can see not only tops of the conductors, but how they continue to the depths, more than 1 kilometer depth. Actually, it's structures which sulfides, massive sulfides associated with the structures. So on the right side, you can see another example with time domain method, direct comparison with time domain methods in highly resistive environment. Time domain can see on early channels, can see some two anomalies, actually, which are the results of near surface alluvium sediments here in small valleys. So And the rest of the section is very resistive. You can see it's more than 1,000 ohm meters. Mobile MT shows the full picture of resistivity differentiations even in thousands ohm meters, including these conductive near-surface alluvium sediments. So these two examples shows how comparison the natural field advantages in comparison with the more traditional control source time domain method. So here's example of direct comparison with ground MT. The copper cobalt silver mineralization at Elizabeth Creek in South Australia. It's around 100 kilometers south of the Olympic Dam deposit, are hosted by flat-lying undeformed shales of late Proterozoic age, and the mineral deposits are composed of sediment-hosted fine-grained sulfides. And we can see here the comparison between mobile MT, airborne mobile MT system section, and ground MT on both sides. It's different parts of the surveys. So ground MT was, because of signal, was limited by 25 hertz maximum, and mobile MT flying during the survey, it was up to 445 hertz. And that's why the near surface resolution is better in case of mobile MT. And actually in line resolution is better because site spacing at ground magnetic tellurics was 500 meters between stations. In the case of mobile MT, 12 to 15 meters, around 12 to 15 meters is stations distance between stations. So this example from Papua New Guinea, it's a part of the big survey over the known deposits. Here it's undermining. The deposits actually, the structure contains high mineralization of gold, silver, and copper. It's a sulfide veins deposit. Here you can see on the geological maps as well. And the resistivity section along the line, yellow lines here, you can see that the vein systems on the surface is controlled by chimney zones coming from the dome structure or batholith in depths of around 800 meters or 1 kilometer. So this is a geological model of the veins from Kora deposit here. So after mobile MT survey, actually the company K92 discovered porphyry system, not only epithermal veins. Geologically, they mapped on the surface advanced argillic lithocap. Here is the contour of the advanced argillic lithocap. It's a length of the lithocap around 5 kilometers. Geologically, argillic lithocaps usually covers the porphyry systems. So, and in the section along this line, or Blue Lake, this is a porphyry system newly discovered. We can see the argillic lithocap on the surface. It's very conductive here. And underneath, it's a potassic core of the porphyry system, resistive potassic core. Very often they are resistive. It's this line. And another line is here with projection of drill holes. And we can see the copper grade section from the drill holes and the alteration zones here. This example from massive sulfides, nickel, cobalt, copper, platinum minerals over a known deposit in Montana, US. Stillwater district. This is a chrome mountain deposit. Firstly, the deposit was flown with time domain system, which is called target AM with 15 Hertz base frequency. We can see very nice anomaly because the deposit is near surface, but depth of investigation is limited here because it's very conductive. It's close to 1 ohm meter, the sulfides here. When we flew it with mobile MT system, we discovered new target under the known deposit near surface. And this new target actually historically was drilled by one long drill holes. You can see here the long drill hole up to 800 meters. And in this place, 50 meters thickness of mineralization. So this example shows the limitation of time domain method in depth of investigation under the conductive cover. Actually, it's under the sulfides known deposit. So this example shows epithermal deposits in far east of Russia. It's a Dukat deposit, which is very rich silver deposit, which is controlled by this vertical structure coming from the dome batholith structure here, and in 3D view how it looks. And you can see that it's more conductive in comparison with more resistive host rocks. On the right side, it's an example of the same type of deposits, epithermal deposits in Kazakhstan. We can see the same dome structures in chimney zone which control known deposits, Zhaysan deposit, or Ungurli deposits here. So you can, petrophysically, you can see opposite pictures. Yeah, it's more resistive on the background of more conductive host rocks, and in case of Dukat deposits, more conductive, controlling mineralization structures on the background of more resistive rocks. But morphologically, they are very similar to each other. If we look at the conceptual model of epithermal deposits developed based on analysis of many deposits over the world, and we can see the morphology, geological model, conceptual geological model, is very similar to what we see in the petrophysics, in the resistivity. And here is more than 1 kilometer depth range here as well. In case of Dukat, it's close to 2 kilometers depth of investigation. So it's another example from Kazakhstan. It's ferromanganese and polymetallic ores, which are discovered and drilled before the survey. We just tested the system here. And we can see the deposit on the plan view is pretty conductive here. And in the section view, the projection of the iron manganese ore and with copper core inside, below the iron manganese ore. So this is very typical example for porphyry systems in northern Chile. So we can see on the left side the resistivity section derived from mobile MT data. Geologically, this is a layer of gravel, resistive layer. Underneath we have a pyrite-rich strata bound. It's barren sulfides here. And below, it's a porphyry system. Actually, it's a potassic core, more resistive, surrounded by alteration zones. Everything, this resistivity sections very well matches with the geological model of typical deposits in northern Chile. So this example from British Columbia over porphyry system, and this porphyry system controlled by a resistive batholith and structure which is controlling mineralization near surface. This is geological model, and this is just two different sections along the same porphyry system. So this is orogenic gold from Kyrgyzstan. It's a Kumtor deposit, and geologically, on the top we can see the graphitic shales, which are conductive. It's 400 meters thickness of graphitic shales, but underneath we can see the mineralization controlling structures, which control mineralization near surface. It's two different lines around 200-300 meters between them. So, and the deposit, actually, erosion level of the deposit is mesozonal level, and we can see underneath alteration zone or apical part of the batholith underneath the deposit. So in exploration, it's very important to see deeper, yeah? Regardless of mining interest. Mining's usually interest is near surface, yeah, several hundred meters. But in exploration stage, it's very important to see deeper. Petrophysically, we can see the source of the mineralization fluids and structures which control mineralization near surface. So this is just example from Sudbury. We can see the conductive foot wall up to 800 meters, so close to 1 kilometer, which control nickel mineralization in the region. So this is a Tabasco Basin example, uranium exploration. In uranium mineralization in Athabasca Basin in Canada is related to unconformity contact between sandstones, overlying sandstones, and basement with graphitic mineralization. And here, the drill holes were drilled after the mobility survey, and we can see very well where the unconformity with graphite and uranium mineralization. So there are several configurations in mobile NT. This is drone modification, and which actually can get lower frequencies and can have deeper depths of investigation, greater depths of investigation, because of low motion noise in this case. So actually, this is what I wanted to show you, and the technology currently is used in many countries and continents, and comprehensive technical solution of the natural airborne AM system makes the system capable and efficient in exploring different mineralization types and recovering complex geological settings and structures. So thank you so much for your attention. This is just our publications in minerals, in geophysics, and on Summit of Drone Geophysics as well. This is what I wanted to show you today.
Thank you, Mr. Alexander, for covering your presentation, a very good presentation, within the time schedule given of half an hour. The utility of the mobile MT technique for identifying the IOCG as well as the gold deposits, giving number of examples. I request from the audience for any queries, please. Mic dijiye.
Hi, Alex. It's a fantastic, very nice presentation with a lot of case studies. Really good to see you. Actually, my question is regarding cultural noise. A lot of high tension power lines, industries, mine sites, how this kind of natural measurements in the noisy environment is how it is affecting. Yeah, this is Karunakar from Steiger Geoscience.
Sorry, can somebody repeat the question because I didn't catch it?
Yeah, question is, Alex, cultural noise, how your mobile MT is doing the kind of a survey in the cultural noise like high tension power lines, mine sites or industries?
Yes, it's a very good question. I know in India it's very, very important because there are many infrastructures and power lines. Yeah, like in all actually electromagnetic methods, mobility as well is affected by power lines. But high frequencies usually are not affected by power lines. I mean, high frequencies above the dead zone, usually it's 4, 5, up to 10, 15, 20 kilohertz. These frequencies usually are not affected by power lines. But it's always difficult to predict. For example, we flew, what I showed in this presentation, we flew over Sudbury structure, which has many infrastructures and many power lines. Usually 200 to 300 meters apart from high voltage power line, the signal is already good from geological environment. So, but it depends. Sometimes we fly even over active mines and we have good data. So it depends on particular power lines, the frequency band, but usually the influence very similar to regular time domain method as well.
Thank you, Alex.
Yes, please introduce yourself. Prior questioning.
Alex, I'm Professor Shalivahan. I just wanted to ask what Karnakar was asking. How are you taking care of both the incoherent and the coherent noise? Which processing schemes are you trying to do?
Current noise, sorry?
Incoherent and coherent, and which processing schemes you are trying to do?
So the processing scheme, actually it's very close to ground MT, except our electrical component is base station. It's stationary electrical component. And we calculate apparent conductivity in relation to the base station. In ground MT, you know, we always moving together, electrical component with magnetic component. Yeah, but in airborne modification, we cannot do it. And that's why our electrical component is stationary. And everything actually basically is calculated as very close to ground MT. And by the way, we don't have the problem with static shift, with static correction, because our electrical component in the same place. So we need to correct like static shift only between base stations. If the survey block, for example, very big, and we need to use several base stations, we need to do the static correction between base stations, between blocks, actually, survey blocks.
Last question we'll take.
Hello, Alex, this is Satyanarayana from Critical Mineral Trackers. So we know that MT is usually using the natural currents and all, but the bandwidth is very low, where low frequencies are being used. can we do any survey under the high power lines, because that is AC current with around 60 to 70 hertz, 50 to 70 hertz. Can we use that as a source, and can we do any, investigation on those areas, taking the source as the power lines?
It's as I said, it's not predictable. It's risky. Yeah, because sometimes we have very minimal influence, but as I said, usually high frequencies in kilohertz, because we cover up to 21 kilohertz, including VLF frequencies, by the way, they are almost not impacted by industrial noise.
Okay,
So, but high frequencies provide only limited depths of investigation. If it's resistive environment, it will be several hundred of meters. But if it's conductive, it will be limited depths of investigation with only high frequencies.
So the hard rock areas are very suitable, what you mean to say?
Sorry, say it again, please.
The hard rock areas are suitable, you mean to say that, which are not conductive?
If the host rocks are not very conductive, the depth of investigation only with high frequencies is good enough usually. Yes.
Thank you.
But yeah.
So thank you, Mr.
Very
Mr. Alexander. Thank you very much. I think RSAS from GSI should gear up to put the queries, since we are carrying out the geophysical surveys, and it is related to one of the topic using the mobile MT surveys and identifying the deposits, IOCG as well as gold deposits. So thank you, Mr. Alexander. We'll move to the next presentation, please.
Thank you. Thank you, Dr. Alexander, for that fascinating presentation on airborne electromagnetic systems and their impact on mineral exploration. Continuing with the theme of innovation, our next speaker will explore how multi-parameter geophysical approaches are improving geological understanding on a national scale.
It's my pleasure to introduce Mr. Mahdi Busaidi, geophysicist at Sander Geophysics Limited. With over 8 years of experience across oil and gas and airborne geophysics, Mahdi brings a unique perspective on integrating complex datasets for more effective mapping. He holds a MSc in Geosciences from the University of Texas at Dallas and an engineering degree in geophysics. After 6 years in quantitative interpretation for oil and gas, he now focuses on airborne geophysical data acquisition and interpretation under India's National Airborne Geophysical Mapping Program.
Today, he will present multi-parameter surveying under the National Airborne Geophysical Mapping Program. Please join me welcoming Mr. Mahdi Busaidi on stage.
Everyone. First of all, I would like to thank GSI for this wonderful and enriching conference. And I would like also to thank the chair of our session. This is Mahdi Busaidi from SGL, and today I'm presenting part of the work we did in partnership with Pan India for the Geological Survey of India under the National Airborne Geophysical Mapping Program of India. Here I'm presenting the work we did in our multi-parameter survey of Block 6. I will also be talking about the importance of multi-parameter acquisition and their role towards an accurate geological model building. So as we see, Block 6 is located in central India. It extends across multiple states and northeast Telangana, and northeast Telangana represents the core of Block 6. Following is the geological setting for Block 6. The general direction for geological features within Block 6 is northwest to southeast. It is mainly characterized by the cratonic boundary of Bastar Craton and East Darwar Craton. The cratons are known for their distinct mineralizations, and the block also houses the large Gondwana Basin, which is known for its coal deposits. The block has also several smaller structures, such as the Deccan Traps and the Godavari supergroups. All these structures represent interesting differences in mineralization and mineral deposits. And to better understand these different deposits, it was decided to conduct a multi-parameter magnetic gamma ray spectrometry survey. The two methods were used for their straightforward use and their proven potential in deposits exploration. Given the northwest-southeast direction of geological features within the block, we opted for a southwest-northeast traverse line direction, which is obviously perpendicular to the geological strike in the area, with the typical traverse line spacing of 300 meters and control line spacing of 3,000 meters, keeping a ratio of 1 to 10. For altitude fly-in, we opted for a drape fly-in, which is optimized typically for magnetic data. The drape fly-in allows consistent intersection elevations and consistent readings of the magnetic data. This way we will avoid noise in the leveling and intersections. With the target altitude of 80 meters above ground level, we are forced to raise the drape above towns and villages and mines. And we raise these areas of the drape following the recommendations that we typically receive from our fly-in and HSE department. In these three panels, we see the Copernicus 30-meter digital elevation model that was used to build our drape. We see also the drape surface to be flown with all the raised areas, and they appear as small rectangles. Sorry. And they appear as small rectangles here. And also we see the predicted clearance before the start of flying. We see that generally the drape hugs perfectly the ground with the clearance of 80 meters, except around the raised areas. Here we are looking at the terrain drape clearances statistics, where 50% of the flying is perfectly matching the target, and up to 90% of the flying is happening below 200 meters. The remaining is flown up to 400, 500 meters due to raised areas, obviously. At the beginning of every survey, each aircraft undergoes several calibrations and tests to extract a broad set of coefficients and to ensure proper functioning of all equipment. There are several mag tests and spectrometry tests as well. As an example of the gamma ray spectrometry calibration, here is the stripping test, sometimes also known as the pads test, where basically we use different concrete pads with known concentrations of the elements of potassium, uranium, thorium, and background to measure how every element is affecting other element energy windows. Another important calibration is the removal of radon. Different methods exist, and we typically at SGL opt for the use of methods that do not require an upward detector. This allows us to reduce weight in the aircraft and constantly be more efficient while flying. We can use the radon spectral ratio method, since the radon is a daughter element to uranium, and due to Compton scattering, it greatly affects the lower uranium window, but it still affects every energy window caused by the decay of bismuth 214. We define the two uranium peaks, we define the ratios, and we strip the radon out of the data whenever it's affected. Another way of doing it is by measuring the radon effect on test lines. Since the thorium is radon free, we see that it's generally constant over the same test line. Here we are looking at data from thorium concentrations over the same test line in different days. So the thorium is radon free, so it's constant. In another hand, we see how the uranium changes from a day to another over the same test line. We established a uranium baseline, the one we see here in red, and then whatever the measure is above the red line generally is the effect of the radon. We try to remove that effect. We can also establish the relationship between the two uranium peaks over the same test line. Any outlier is typically the effect of the radon. After we establish the relationship, this can be a good way to check of our radon removal. So the upper to lower uranium relationship can be established from the PAT tests also. So here we have different methods shown that can be used alternatively to remove the radon effect and cross-check the quality of the radon effect removal. The stripping that we are doing, we can say that, confidently say that we are doing a good job in removing the radon effect without the need of an upward detector. And these features aligns perfectly with today's workshop vision to use advanced techniques for better efficiency. The final data processing and interpretation were performed by our geophysicists at the APIC Center at the GSI office in Bengaluru. The final processing includes a wide range of data treatments, and here we're seeing an example of the removal of trees from terrain altimetry data. We see in this example how we go from a forest-covered area to a bare earth model with no trees. Here we see the complete bare earth terrain grid over the whole block. This process is not only performed for aesthetics purposes, but it's also a way to QC for the height data that will be used both in mag processing and spectrometry processing. For the magnetic data, we have several output maps. First, we are looking at the magnetic intensity. The map gives already an idea of some of the geological structures. And as we expected, we can see a very big south-north gradient, which is mainly due to the increase in intensity the closer we get to the poles. Then after removing the IGRF model, we are left with the anomalous magnetic intensity. We already see several geological features. We see clearly the highly magnetic active cratons to the west and to the east. And we notice as well a very low, or I would say more constant values of magnetic anomaly over the sedimentary basin. The three magnetometers on the aircraft constitute our magnetic gradient system. It allows us to calculate the lateral and longitudinal magnetic gradients. Again, the mag gradients require also a series of more careful corrections, more importantly, the yaw correction, and other corrections performed depending on the needs. And here, since the Gondwana sedimentary basin, as we have seen earlier, since the Gondwana basin displays more regional change in anomalous magnetic intensity, we see that its gradient values are closer to zero. Basically, all the yellowish, greenish colors are really close to zero. These gradients, and since they have a differential character, they allow for a better visualization of narrow geological features, such as dikes in the north and some faults that we see here. And also, we can see human-made anomalies, such as this railway. And we can see also pipeline, obviously. Here is the longitudinal gradient. The same features look, but slightly different. We can see the same features, but in a slightly different way. And here is our in-house enhanced magnetic anomaly. We usually build it by combining line data with lateral gradient. No filtering is involved in the enhancement process. We see that we reduce aliasing, lateral aliasing, and we give a more complete aspect to the anomalies. Now we move to the gamma ray spectrometry different outputs. This is the gamma ray total count limited at 375 meters of height. Obviously, because above that we start losing counts. There is also the potassium percentage or concentration. We can already start seeing the different signature of the two cratons, meaning that they have different mineralizations. We see that the Darwara craton to the west has a higher potassium content compared to the Bastar craton to the east. Thorium concentration, which is often correlated with more felsic silica-rich rocks. We obviously see it in the Gondwana basin. Potassium, uranium, and thorium. Yeah, so here we see the high signature of thorium in the Gondwana basin, which correlates typically with high silica and silica-rich rocks. Then we go through the different ways of looking at spectrometry data with different ratios, equivalent uranium to equivalent thorium, and each visualization gives an additional piece of useful information. Here we are looking at the cyan, magenta, yellow ternary map. It gives more information and it allows us to compare the presence of different elements or the relative concentration of each element in separate radioactivity wind ranges. Here we can see the RGBK, basically the dark color is completing the RGB colors. Basically the dark is weaker values and the more colorful things are the higher radioactivity we have. So from the previous slides, we see that we are able to discriminate between different geological rocks and features through ranges of values. And we are not able to put a fixed value on each rock. The magnetic mapping quantifies magnetic susceptibility, and which is directly proportional to the magnetite concentration and the magnetite content in the rock. In this slide, we see also the how the magnetic mapping is characterized in the rocks. And since the magnetite is the most magnetic and most common mineral, mapping the magnetic is in effect mapping the percentage of magnetite in our rocks. In the gamma ray spectrometry, the surface of the three elements contents is measured, and the gamma ray spectrometry has no depth of penetration. And while using it, we should always keep in mind the shielding effect that the surface can have on deeper deposits, and the effect of host alteration. Here also we see how the gamma ray spectrometry characterizes different rocks in ranges for all the elements. In addition to and to narrow down the answer in identifying clearly the rocks, the density can also be used in mapping in our mapping through the gravity. Our gravity system has a 0.1 milligauss sensitivity, which translates to 1% of a gram per cubic centimeter accuracy. But also, the low geological contrast in density always makes it harder to separate rocks. This high sensitivity tool can be great for instances where other properties don't have much change or change regionally. This is typically seen in sedimentary basins. It should have a great added value in mapping regional structures in sedimentary basins, typically in our case in the Gondwana Basin, or it can be also used in the Ganges Basin in the north. Here we see the density ranges covered by different rocks and minerals. Again, we see that there is not much contrast in density, and the density range is pretty small, going from typically 1 to 4 or 5. So here, to map the density, you need really high accuracy sensors. An additional rock property that can be mapped is the electrical conductivity. The electromagnetic method covers large ranges of resistivity, and we usually think that this is a very good way to discriminate and separate between different rocks. Here are some of the rocks conductivities, and we see we keep in mind the very large ranges covered by this method. Sometimes it allows for an easy pinpoint to a mineral or rock of choice. We keep in mind the ranges that goes from a very small value to millions of in order. To highlight the edge that airborne exploration has over ground geological mapping, here is a quick comparison, where airborne surveying allows an efficient, high-resolution targeted mapping by focusing just on the anomalies that we are interested in of specific and key rock properties, while the geological mapping is not as efficient since it maps as much data as possible without really focusing in specific ranges, which is typically slow, all while being done in a very low resolution. Basically, we cannot get what we want from the data. It's the geology that will dictate what we will have as output. Here also we see a summary of different rock property ranges that we covered earlier, where best characterization is typically achieved with high sensitivity sensors in narrow rock properties such as the gravity, Basically here, where we don't have so much change, we need a very high sensitivity sensors, and we need also a wide range sensitivity sensors in methods that have a very wide range as well. Typically, we see that in the EM method, that is quantifying the conductivity and resistivity. Here I wanted also to summarize the role that played by geophysics in the world of geology, where geophysics provides the quantifying tools for our key properties that we want to measure. Most of the focus basically has to go to the measured properties, and we should not really focus much on the method that we will be using. The quality of the study and overall efficiency is also achieved by identifying those key properties that we want to measure. This is something that we always need to keep in mind as geophysicists and not get carried out by the methods that we are using or how good they are. Once we know what we want, and once we know the key properties that we are trying to measure, measuring them all in one shot is the greatest way to cost-effective and efficient mapping. We can see here the overlap between two rocks in one property, let's say the density, where we see there is a huge overlap between the two rocks. Basically, in 50% of the cases, in this case, we cannot say which rock we are measuring. Including a newer key property to measure will help us getting closer to the answer, and including an additional property to measure will help us narrowing down the answer even more, making it the closest to reality. At SGL and throughout the years, we have successfully combined the mapping of multiple physical properties, all in one shot, by embedding multiple sensors in a single aircraft. And this aligns perfectly with this workshop vision of sustainably maximizing the resource exploration in an efficient way. Thank you everyone for your time and attention.
Thank you, Mr. Mehdi, for having a nice presentation.
Thank you so
on
much.
the NAGMP survey being carried out in Block 6 of GSI.
Yes.
From the audience, I would like to have some queries on the presentation. Please, Mr. Patan, please. Mic dijiye.
Good morning, sir.
Hello, sir.
Are there any advancement in aerogeophysical survey to reduce ambiguity in kimberlite identification? Because as we know that kimberlite gives non-unique signatures. Sometimes it gives low. I'm not audible to you?
A little bit.
Okay.
Yeah.
Are there any advancement in aerogeophysical survey to reduce ambiguity in kimberlite identification?
In radioactivity measurement?
Sorry?
In spectrometry
all, because for kimberlite we use conductivity also, magnetic signatures also, gravity also, as well as radiometric also.
Yes. Basically, typically we try to stick to the proven methods, and we try to pinpoint the right properties that are needed to really know which rock we are targeting. Basically, we focus on the properties, and the right combination of the methods will help us define and characterize in a better way our rocks.
Sir, in many cases we saw that this kimberlite gives low conductivity.
Yes.
And as well as low magnetic signatures. So, but
Using EM, to answer your question, using EM can have a big role, especially if we opt for frequency domain EM that has a better visibility in depth.
okay, okay.
Yeah, and it allows us to discriminate. As we have seen, we have a range of a very wide range of values in conductivity. That using frequency EM will allow us and help us get a better understanding.
This potassium radiometric that in the radiometric survey we do this potassium count. So how much it is important in identification of kimberlite?
So the kimberlites are felsic rocks. The potassium will have an addition. The potassium concentration will have an added value. It will show an added value, but the issue with any radiometric method is the depth of investigation. We're basically looking at just the surface, the couple of centimeters. We are not seeing deep. Basically, if you have a deep kimberlite, basically you can be sleeping on diamond and without noticing, because it will not help you much see it in the surface. You will not be able to see much if it's not visible in the surface. Okay. If it's covered just by weathered soil or any vegetation, that will prevent you from seeing it through spectrometry.
Thank you.
Thank you so much.
Next question, please.
My name is O.P. Somani. I am from Ballota Group. So you have flown to Bastar Craton as well. So did you identify that pegmatite belt? It is a long pegmatite belt, 70 to 80 kilometers. So what are the signatures?
Yes.
And what is the follow-up you are suggesting there? Because it is full of critical minerals there in this pegmatite belts.
Yes, I remember seeing that in our final interpretation report, and you can access that through GSI as well, because we have submitted it to GSI. We've seen that belt, which were typical of a lot of iron ore deposits, and we have seen also a high uranium in that area. Yes, that's the high uranium was the biggest thing that we characterized this time in that area, and we have submitted as well some recommendation for additional studies of that area. Since the uranium is typically hard to find in a very regional surveys like this, we submitted an additional recommendation for more uranium investigation in that specific area.
Yeah, there are a number of uranium anomalies also identified there, and this atomic mineral division has drilled there also. So that is also true. Yes.
Yes, thank you so much.
Any query, please? One from my side. Mr. Busedi, one from my side.
Yeah, sure.
In your abstract you had given, exploration success can be improved by using multi-parameter approach.
Yes.
We had carried out NAGMP in block 6. You had mentioned about this multi-parameter approach, airborne gravity data by air graph system.
Yes.
Then frequency domain electromagnetic data by SGFEM system, gamma ray spectrometry, and magnetometer survey.
Yes.
So we do have a multi-parameter approach, or somewhere GSI is missing to have an integrated one?
No, typically we just wanted to highlight the way how they can all play together, and every method and every parameter that we will be surveying adds a value. Basically, I understand that GSI has a knowledge of all of them and using them all, and we would like to see more combination of these properties working all together. That will make the interpretation much fascinating and much accurate. And we will have not just guessing of the model of the Earth, but we will have a closer to reality model.
Okay, thank you.
Thank you.
I think anybody from RSS? Time is over, but I will permit one query. Please.
Yes, so just I am adding on your questions, what you have asked. So we are suggesting...
Please introduce.
I am Naresh Agarwal from Pan India Consultant Private Limited, partners with the Centers Geophysics Limited, which is represented by Mr. Mehdi. So we are suggesting GSI from last many times to integrate all the 4 sensors, that the EM, gravity, magnetic and radiometric in a single survey. So that's possible. They are already flying in Oman and Ireland. So they have like integrating all the sensors in a single survey have a distinct advantage on just flying in a magnetic and radiometric. That's what I want to add that much. Thank you.
Okay.
Exactly. I would like to add a small point. Yes, we have conducted such surveys in multiple countries. We did them in both regional scale, covering basically whole countries, and we did them on very small areas. And every time we have seen an added value. It's true that sometimes it comes with a few logistical challenges, but since we have experienced and we did several projects in this way, we are familiar and we can say confidently that we are able to conduct a very complete and multi-parameter survey.
But modeling with all these 4 parameters,
yes.
What is the outcome, the output?
The outcome is a model that is closer to reality. So we don't want to just start and using a method and then we just push it quickly to inversion, and we push our partners into the game of guessing and having not a very accurate model. So we would like to pinpoint our model in a very accurate way using proven methods and proven science. That's what we typically try to do.
Okay, thank you.
We try to stay fiddle to our partners and fiddle to the science basically.
Okay, thank you. I think RSS needs to look into it. One last query. I'll permit Mr. Srinivas. Mic दीजिए.
Hello, sir.
नहीं mic दीजिए.
You have worked in this block 6.
Yes.
So my question is in a general way. For this type of latitude and longitude, what is your experience elsewhere regarding RTP and RTE maps compared to the TMI map?
RTP, reduction to the pole and reduction to the equator, right?
Yes.
Yeah, usually we have a very straightforward way of doing it, since it's really defined by stable equations. So typically if we do an RTP and RTE, that will be just an additional tool of interpretation of our anomalies. And basically it's just when we are looking at the same anomaly, we will have 3 different ways of looking at it, and that will allow us a better understanding of that anomaly. Basically when we are moving the intensity.
Okay.
Thank you so much.
Thank you. Thank you, Mr. Mehdi.
Thanks
I
to
think it's time to move to next presentation.
Thank you so
Thank
much.
you.
Thank you.
Thank you, Mr. Mahdi Busaidi, for that presentation and answering so many questions from our audience.
Ladies and gentlemen, an important announcement. You are going to have an international seminar on unearthing the past, shaping the future, which will take place at Jaipur in the month of November. To let us inform more about that seminar, I would like to call upon stage the representatives from GSI Western Region on the podium.
So please.
Please welcome Maurya, sir.
Good morning to all. We are happy to announce that Geological Survey of India Western Region Jaipur, under the overall patronage of the Director General, Geological Survey of India, and under the aegis of Ministry of Mines, we are organizing an international seminar on unearthing the past, shaping the future, 175 years of GSI. So for this international seminar, I am extending our invitation to all the private exploration agencies, all the people from academia, people from the industries, and the people who are interested in the field of geoscience, research scholars, and students for the participation and for a bigger participation. And we are providing the opportunities to interact among ourselves with the people from the international level during these seminars. So it is a good opportunity. So I invited all the people from different fields and different organizations to participate in this seminar to enrich the knowledge in the field of geological investigations. And we have various themes. So here, so these are the sites. From here you can get the information regarding these seminars. And this at present, the abstract submission is going on, and the last date for submission of the abstract for this international seminar is the 30th June 2025. So now only less than 1 month is left. So kindly expedite the submission of the abstract for the seminar. And we were little late, but now the registration is also open, so people can register for these seminars. And our abstract has to be submitted through the site of Geological Survey of India. This page, once the home page, you go to home page of the Geological Survey of India, and there is one icon for this international seminar, and from there if you click, then this page will be opened, and from here you can submit your abstract for this international seminar, and we are allowing only through this website for the submission of the abstract. No physical submission of the abstract, only through this site you can submit your abstract. And this is the venue. This is the Rajasthan International Center, Jaipur, a nice place and a good place. Here we have the different halls. We are planning to carry out 3 parallel sessions because we are covering a wide area and in this seminar. So we are planning to conduct 3 parallel sessions on the different themes for this seminar. So we have booked 3 halls for the conducting this seminar at the Rajasthan International Center, Jaipur. It has a good capacity for this. These are the few photographs of that center. And this is our first circular. It is out already, and we are in the process of just issuing the second circular, in which more details regarding this international seminar will be provided and different accommodations. The time period is 20 and 21st November 2025, a pleasant time in Western India, and the weather is very pleasant, very good. At that time, overall, the average temperature is around 20-25 degrees, sunny sites, sunny seasons. And historically also, this Rajasthan is also a very well-known place. Jaipur is well-known place. So it is a nice opportunity to visit this place and participate in this international seminar. We are also planning, if time permits, to conduct outfield, and after completing this seminar, so some excursions we are also planning, if time permits us. in some important geological sites in the Rajasthan. Thank you.
Thank you so much, sir, for letting the audience know about the seminar that is going to be held in Jaipur, and I think all of us can look forward to it. So as we have just explored these advanced airborne geophysical methodologies, this presents an excellent opportunity to reflect on these concepts while networking with colleagues. Before we continue with our next session, we will now take a short break to recharge and continue to these important discussions. So ladies and gentlemen, we'll pause for a 10-minute networking tea break. So this is a great opportunity to connect with your fellow participants, speakers, and colleagues over some refreshments.
We kindly request everyone to reassemble in the auditorium by 11:30 sharp, as we will resume the session with next set of presentations. Thank you and enjoy the break.
इलेक्ट्रॉनिक कर रहे हैं।
The Geological Survey of India, under Mission 1, is leading the national effort to create a comprehensive baseline geoscience database. This foundational initiative supports mineral exploration, scientific research, and strategic planning for India's long-term resource security. To fulfill this vision, GSI employs a combination of traditional field techniques and advanced survey technologies. Among the most transformative recent innovations is the drone-based magnetic survey. These high-resolution, low-altitude surveys allow geoscientists to gather precise magnetic data with minimum cultural noise, and over vast and inaccessible terrains. They detect subtle magnetic anomalies near the surface, key indicators of hidden mineral deposits. Mission 1 is more than a data collection exercise. It is a transformation of how India understands and utilizes its natural resources. It represents
all are requested to please kindly reassemble to the auditorium. We are going to resume the session shortly.
Sri Vikram KY Critical Mineral Trackers. A huge round of applause, ladies and gentlemen, for Sri Vikram KY.
Hello. All of you are requested to kindly be seated. We're going to resume the session in next 2 minutes.
The next commodities are manganese, graphite, REE, cobalt, and associated mineralization, and it has been allocated to Mrs. Critical Mineral Trackers, CMT. Mr. S. Uma Maheshwar Rao, Director Exploration, is requested to kindly come up on stage. RMT for manganese, graphite, tungsten, cobalt, REE and associated critical minerals in part of Alluri Sita Ramaraju district, Andhra Pradesh.
Welcome. Ladies and gentlemen, welcome back. We hope you had a refreshing break and enjoyed the opportunity to network and engage with your peers.
Now we look forward to continuing our day 2 session of Next Gen Geophysics 2025 with more insightful presentations and thought-provoking discussions. We kindly request everyone to take their seats, settle in, and join us as we resume our next speaker.
So to begin with the proceedings, it's our honor to invite the session chair of the forenoon session, Sri D.V. Ganveer sir, Additional Director General, Head of Department, Central Region, and National Mission Head to Geological Survey of India. Sir, please. It's our pleasure to resume the technical sessions with a presentation by one of the leading voices in geophysical innovation, Dr. Jeff Ketley, CEO of Interpret Geophysics. With over 25 years of global experience across mining, petroleum, CCS, hydrogen, and geothermal sectors, Dr. Ketley has been at the forefront of applying geoscience to real-world resource challenges. His expertise spans seismic interpretation, gravity and magnetic modeling, geophysical inversion, and the development of common Earth models.
A pioneer in integrating AI and machine learning into exploration workflows, his work supports scalable multi-resource discovery aligned with the uncovered vision for deep cover and responsible exploration. Today, he presents on AI-driven geophysical modeling and targeting, transforming mineral exploration from data to discovery. Please join me in welcoming Dr. Jeff Ketley virtually.
So Dr. Jeff?
Thank you very much.
Yeah, your screen is visible.
Can you hear me okay?
Can we have an audio check? Dr. Jeff, can you have an audio check? Can you speak?
Yes, talking.
Yes, you're perfectly audible.
So you can start.
All right, let's go. Thank you very much. Firstly, thank you for the honour of presenting today in front of such esteemed GSI directors and key staff. It's been a long road for me over the last 25 years. I've travelled to India must be almost 20 times now, and it's such a beautiful place. Anyway, let's kick things off. So Intrepid Geophysics has 35 years of exploration in mining and petroleum technology, and the key aspect historically before I took over was about advanced processing. But in the last 6 years since I've taken over Intrepid Geophysics and working with leading AI groups in Australia, we've focused on decision-based targeting and decision-making. In short, not all geophysics products are equal. So historically, you can see here on the graph, I'm going to focus today really on the Cauchy geophysics. Can you see my mouse? I assume so. In 2022, and I'll run through this briefly because it's a very short presentation. But all aspects of geophysics has been touched by Intrepid over the last 35 years, and I'm excited to be leading the company. So as we know, there's an increasing global demand for critical minerals, and traditional methods, such as what I call retail technology, are really fronting up to real challenges. The requirement for countries to target deeper, undercover, with greater geological complexity in more complicated terrains challenges exploration companies and governments to find new targets. And with the shortage of some supplies of resources, there's a really critical focus on speed to discovery, from data to discovery. So from Intrepid and Sensor, we expect there to be a new paradigm shift, which is not just AI and machine learning, but in fact, new tools, new workflows, extracting geoscience from geophysics. And the key focus for our business today is reducing risk, improving accuracy, and accelerating undercover discovery. So in Australia, the challenge has been, over the years, all the easy mining targets have been found because they were at surface. So what we prioritised was what data sets enable high fidelity, volumetric geophysics under the cover. And I must add to this that in AI and machine learning, the critical input for geoscience and exploration is really the geophysics, because it is the volume of data that sticks everything together. So very briefly, I'm going to run through gravity, magnetics, and electromagnetics, just touching on reflection seismic today. But what I want you to take away is there are multiple approaches to AI. There are approaches that use images, there are approaches that use grids, and there is what we propose today as geophysics volumes. And what we're doing within this workflow is applying in the order of 50 automated tools that enable you to target undercover, identifying structures and rock properties using things like stabilized downward continuations and higher order derivatives. And this, of course, is always linked with geological testing using joint stochastic inversion. So all these tools that I'm going to talk about today are automated, so you can plug and play them into your AI workflow. It's not agnostic. They're commercial. Every day in this business, we run 5,000 tests on our technology to make sure that all our tools are stabilized and are providing the best solution. In addition, everything that we're talking about here is fully documented. So to kick things off, everyone talks about large scale. For 15 years, Intrepid Geophysics has been managing and working very closely with Australia's leading geoscience group, Geoscience Australia, that has done a sensational job at attracting investment into the country by managing data and working with experts to extract the best information possible. On the left, you can see the density of ground gravity. On the right, you can see the seamless image of magnetics. And you think that, oh, well, once we build this, it's done. Every 2 years, we rebuild this. We improve the data, we add new data to provide to the public so they can make the best decisions. This data set, when we're working in exploration, needs to scale. It needs to scale from continental all the way down to deposit scale. Now, this is done in this case using grids. During this talk, I'm going to differentiate between grid-based approaches and located data approaches. And it's a little bit unconventional because everyone loves to do 3D modeling. So just to give you an idea of, a couple of years ago, we did a review of the magnetic data of Australia. This is giving you an idea of the coverage of line spacing of greater than 70 meters. Now for Australia, that's quite a lot. But does it really mean anything, right? We have all these old surveys, of course they are. We've got 70-meter line spacing. What happens when we overlay surveys with 40 meters or less, or between 40 and 70? You can see Australia is covered almost entirely of geophysics data, in this case magnetics, that is 40 meters or less. The yellow or orange areas is 40 to 70, and the red areas, there are only a few left here, in the offshore and in the west and in the southeast, where the spacing is 70 meters. Now you might say, well, so what? Well, when you're doing an AI workflow and you're looking at your products, your grids of geophysics or your data, you need to have an understanding of the uncertainty around the geophysics. What height was the data collected at? What was the equipment that was used? And are there any limitations? So what we also do is enable decision-based products like this that enable you to look at a risk-segmented version of the data, giving variations in quality. Because just because we produce the national grid of magnetics or gravity or radiometrics doesn't mean that all points are equal, all areas are equal. And so, for example, with Geoscience Australia, they would use this type of tool for planning to acquire new data. So something that I'm going to focus on today is a new form of exploration. And this is using Cauchy-based complex approaches. And that is not using traditional signal processing, but using Cauchy-based complex approaches using complex numbers. Everyone probably knows this. What this is a fourth order spectrum. You can see here, the blue zone is a traditional fourth order derivative. The central image shows a grid with stacked profiles with no real coherency in the black lines, which are the stacked profiles. On the right, you can see the Cauchy fourth order complex derivative. And what's interesting there is you can see a series of horizontal, thicker, fuzzy lines and a complex geometry that goes from the bottom in the middle all the way up to the top. Now, what that's actually showing you in the Cauchy domain, you're getting these higher frequencies in the complex domain, which is generally around 30% more information in your derivatives. In this case on the right, there is in fact 2 drill locations formed on this geological contact that was drilled in Canada some years ago. So the challenge here is, if we use a grid-based approach, it's really interesting in the background, you can see the colours, but there lacks the precision, the fidelity to look at a pure contact. Now, I'll explain this further in the next slides. So what I'm going to do is scale. So when we're doing machine learning and AI, we're using continental geophysics, and then we're scaling in to critical areas. This is in Victoria, the Bendigo area, the southern half of this circle. The light yellow is exposed generally, and as it goes towards the more khaki colour, here, where it's Fosterville and the red Bendigo area, you're going undercover. So you can see all the discoveries in the lower half, but where are the discoveries in the north? The reason there aren't many discoveries or mines is in fact because it's under a cover of over 200 metres to say 800 metres depending on the zone. So what we're going to do, what we use is the geophysics from the continental scale to scale in and look undercover. So this is a ground gravity grid of that Fosterville zone, and Fosterville is located about here where my mouse is, if you can see it. Now, on the left, you're going to see one product, and on the right, you're going to see one product. Each product is a 3D complex derivative. So the ground gravity is from variable space data points of 250 metres to 800 metre point spacing. So when we run what I call a retail third order complex derivative, you get a relatively clipped, non-geological product. When you run a Cauchy complex derivative, you produce a geological interpretative product from the ground gravity. To point out a couple of things, in this area, everyone interprets north-south faults. Nice, smooth north-south faults. But with this, you can see that there are northwest, southeast faults. You can see that there are buried channels. These are 200 metres to 400 metres undercover. So this is giving you the sum of the the third order derivative from the ground gravity data. It's high fidelity. Now remember, Cauchy is preserving 30% more information. And that 30% information enables you, a geologist, to interpret your geophysics. And as much as I love geophysics, I want my products to be used. And in the last 6 years, we've been focusing on turning geophysics into geological products for geologists. So this is a zoom in. You can see here on the left how much of that area has no real discoveries. In fact, we can do something even more exciting. We've got a third order derivative. Most people, when they're doing exploration, they'll do a first vertical derivative or a second order, maybe. We can do an 11th order derivative. To give a little bit more information, the white are intrusions, but there's more to this story. What does the geophysics look at 400, what does it look like at 400 meters? Well, you asked, like I suggested, the left is what we were looking at before. You can see the channel. On the right, you can see a downward continuation. And that downward continuation is 400 meters undercover. Now, what's really exciting about this is there are a series of east-west features. Now, originally I thought, oh, are they just gridding artifacts? But after very close identification, they are geologically sound. And what's even more exciting, and you can see, you probably can't see, there's been a new discovery here and a new discovery here, both just north of these east-west faults. This is groundbreaking, next generation geophysics. If you try to do a downward continuation on a grid, you'd normally be able to downward continue it, say, about the cell spacing. We can downward continue this data to 1,000 meters if we wanted to. So what this does in our AI workflows gives us high fidelity, depth, undercover targeting solutions. And this is just old data. This is data collected over 30 years. But what more can we do? So we can do high order derivatives, third order, fourth order, fifth order. We can complete downward continuation on magnetics and gravity, airborne and ground. And we can stabilize it to kilometers. But how do we get more information at depth? We're spending all this time in AI and machine learning trying to predict things at depth, but everyone's using what I call a flat Earth grid or a flat Earth image. So what we've recently done is we're now running Archie downward continuation on located data. So this is a very simple schematic. Traditional approach is you take your points, airborne data along a series of lines, you resample it to make a grid. Within that, you downsample your input data because of the line spacing. What we propose today is you take your located data, your points, and simply downward continue those points to whatever depth you think is important, then interpolate between them to make a volume. So what this does, Couchy preserves the data and the information, both amplitude and frequencies, measured along the line. So everything I'm going to show you preserves every point, input point, from your magnetic and gravity surveys. This is from Western Australia. It's an unconventionally coloured magnetic survey. What it is all one large airborne electromagnetic survey, downward continued, 650 metres. Now this area, every point that was collected along the airborne survey has been downward continued, providing an insight of what is the geology at depth. And what I've done is I've taken one cross-section along here, and this comes from up in the northwestern portion, and you can see the geometry of these domes. Now this area has Winu, Telfer, Avalon, world-class nickel gold discoveries. But generally when people do their exploration, they're just simply using grids. Now, if I've taken this as a 2D section out of this whole survey. This one data set is around 1 terabyte of points. Now I've converted it to seg-y because it's nice and simple for me. Here's another one. In Queensland, Cannington. Cannington mine has historically delivered 7% of the world's silver. It's a silver zinc mine. Now, we took, again, a 50-metre magnetic survey and downward continued at 5 kilometres. Now, this is preserving every point, and look at the geometries that you get. Beautiful fold, some faults. a fairly strong basement step, another fold. And you know the exciting thing about Cannington, it's an antiform, it's a refolded fold. And in fact, it looks much like this feature here. And this is just from old, 10-year-old magnetic data. Now, if you showed this lower 2D vertical section to a geologist, they'd say, oh, wow, I can see the geology. And that's my job, right? My job is to help people see geology and geophysics. Then the AI workflow is no longer a black box. So this volume is around 240 kilometers by 240 kilometers. And goes down to 5 kilometers. Now, earlier I briefly touched on grids, and then I brought up located data. This is a located data section, it's just points. This volume in here is a grid-based downward continuation. But if you see the grey and brown-based colours here, that is trying to image this anticline. So what you're looking at here is a 3D view of this anticline, but the grid-based approach doesn't image it, but the located data process does. Now what that says to you is, if you're only using grid-based exploration techniques, you're potentially losing 50% of your targets. That's a real concern. So what we do within our AI workflow is use both grid-based downward continuation and located data. To stack on more geophysics, you can imagine you can run that downward continuation on the magnetics and the gravity, airborne and ground. So you could have 4 volumes of magnetic susceptibility, or 2 volumes of magnetic susceptibility and 2 volumes of density. And then you can stick all your geology inside of it and start to query it. Because the geophysics is the thing that sticks everything together at depth. Here I'm adding another level of geophysics, the airborne electromagnetic solution. Generally speaking, from my point of view, we're only using half the data in airborne electromagnetic surveys. So the top section is a 2.5D solution, and the one below is just an example of 1D. So in Australia, publicly, you can get 1D solutions for free. But if I wanted to drill a target on the 1D solution, it's a little bit complicated. But if you do it on the 2.5D solution, you can see that there are clear drillable targets in the yellow circle and the white circle. Now, this is well known, 2.5D, 3D, 1D. But what people aren't doing is making use of the magnetic data associated with an airborne electromagnetic survey. So when someone acquires airborne electromagnetics, they normally get magnetics. So that means you've got co-located airborne electromagnetics and magnetics. So 2 geophysics responding to different geology. So what you've got here, the top section is the 2.5D AEM. The middle section is the Cauchy downward continuation of the magnetics. And then the third section is an overlay of both, which is really quite fascinating. You can see here the circle on the right, there's a coincidence of both the Cauchy anomaly, the downward continued Cauchy 2D section, and the AEM. So what this starts to do is build a geological section, but a geophysical section for us. And what it means is we're looking at more geology, not just, for example, the magnetite, but we're also looking, for example, at the sulfides or other important geology. Now, if doing one section like this is really simple, but Australia is covered in airborne electromagnetics. So imagine having a cross-section of airborne electromagnetics, a cross-section of magnetics, and a cross-section of gravity. And then you've got thousands of lines. This is where machine learning hits the road, the rubber touches the road, because it's too much to look at using traditional desktop studies. This is why machine learning is very important. One more example before I start winding things up. Here is a lot of the seismic data that we use is confidential, but here is an example of an airborne electromagnetic signal response on top of the seismic. Here's one with the downward on the right, you can see here gravity, downward continued overlaid on the seismic. And you can see that seismic is often acquired for reservoir level or within a couple of kilometres. What you do when you add a volume of gravity or density, a volume of magnetics or magnetic susceptibility, you can see here that there is actually a step. So the white to blue is the gravity, where the white shows you the steps in the basement, where the seismic in the background is just flat. It's beyond the limit where you're just looking at noise. So what we're doing now is by changing the paradigm, giving and respecting the Z component and downward continuing magnetics and gravity and producing vertical sections and volumes of airborne electromagnetics, is we're enabling true multi-physics. So what's exciting about that is that you can stack them together and look at the uncertainty of the sources within a joint stochastic 3D modeling package. Now, just because we've defined all these sources, we haven't actually worked out which way the geology is, which way up the geology is, and what the sources represent. So what we do is we've automated GeoModeler so that you can incorporate 3D joint stochastic inversions with geological rules. So you define the geology, you put rock properties in, and you define the relationships between the formations. And what that does is tests the likelihood of the most likely model when you tie the magnetics and gravity and the geology together. So the image on the right is showing the joint stochastic model varying as it calculates the most likely model. Now, the important thing here, this is our workflow that we use, and it's quite complicated. And I'm only really talking about the section on the left here, complex multi-volume geophysics and geological modelling. But what we've done is we've created an atlas of Cauchy-based discoveries across Australia, and we're extending that across the world for training models. Now, remember this, we're giving volumes of geophysics into our AI. We've automated it, and what it does is it enables the user to test multiple solutions really quickly. Most AI machine learning workflows, you manually produce a product, you put it in there. For Sensor that we work with on a daily basis, we produce all the products of Australia in 3 minutes. The traditional geophysics. To run the Cauchy-based complex derivatives and downward continuation for the country, it takes 4 weeks with around 1,000 CPUs. But what's important about it is we're creating an undercover solution that allows everyone to stick their geology, their geochemistry, their drill hole data, the rock characteristics, any other type of geophysics. And we're creating a volume that enables things to be trended undercover. And we're having a lot of success. So I'm just going to finish this off with a brief statement. One of the challenges with traditional AI machine learning workflows is they're not automated. They're not commercial. But what that means is the geophysics people build the geophysics products, and then they add it to a folder, and then it runs into the system. Then the geochemist says, well, or the geologist says, can you run a higher order derivative or a high resolution product? And then the team have to get together, make it, and then put it in. The solution and the technologies that we're using in Intrepid and Sensor are already available to plug into your workflows. So you put your data into a folder and you can query your data and produce live products. What that does is help groups and teams work together and customize and test different workflows to produce high quality products. Automation is critical for good science, repeatability, so you can go back and look at what were the variables used. Did you run a VRTP or just an RTP? Did you run a volumetric grid-based approach or a located data approach? Because the challenge we see in the market is when we produce a product, clients say, but we don't want a black box. Well, we show them the volume of Cauchy magnetics and gravity. We show them the magnetics. We show them the geological map. And we show them how different our products are to what you get in the market. And what that does, it enables you to use new tools, customizable workflows, and increase the chances of your discoveries by removing and addressing your uncertainty. Thank you very much.
Thank you, Dr. Jeff, for a wonderful presentation on AI-driven geophysical modeling and targeting. I request the audience to please for any queries. Mike, please.
Excellent presentation on the current state of our technology. I have a very small query that how this AI/ML handles overlapping parameter. Say if you are dealing with racivity, how this overlapping range of racivity is used to translate into your parameter of interest. Am I audible?
I'm sorry, but I can't hear anything. Could someone repeat it? Because when you're speaking on the stage, I can hear it, but people in the audience, the volume is so quiet.
I think he's not getting your query.
Is it okay?
That's better.
Yeah.
Yes, thank you.
Yeah. So once we are trying to translate geophysical parameter into say geological parameter or lithological interpretation.
I can't hear you.
You can't hear?
You've gone quiet.
One thing we can do.
If you could repeat it, I can hear you very well.
If you can come on dais, you want to? Or otherwise we do have one suggestion. I think from the audience, I think a number of people might be shy asking the questions and we do have the limited time. We can have those queries and put it to the mail and get it.
That's a great idea. I'd love to do it, and if you'd like, I can run another session of questions and answers.
Can you hear me?
Yes, I can hear you very, very well. Very clear.
Is it okay?
Yes, I can hear you wonderfully, yes.
So, I mean, see, the entire purpose of geophysical application is to ultimately translate into geological or lithological model. Okay?
Yes.
So, how do you handle the overlapping parameter? Let's say resistivity, like if you get the resistivity parameter from the airborne, or any other parameter, how do you handle? Because same range of resistivity at different locations may represent different lithology or geology. And once you take a larger area, how do you handle this overlapping range of resistivity while translating? Am I clear?
Yeah, no, good. Yes, very, very good question. Two answers to that. With our traditional magnetics and gravity-based approaches, we can do full resolution at continental scale. So we don't vary our products. All our products are full resolution. With regards to resistivity, or well, let's say with airborne electromagnetics, we preserve every point. However, with resistivity, not one of our core tools, and that's done, the resistivity work is done by one of our partners. So I can't speak for the resistivity, but when it comes to scale, the process for looking at the potential field geophysics that we run and the airborne electromagnetics, it's just a question of processing and time. Currently, we're running a project, an international project, and it's 4 months of processing on 500 CPUs. So we're not worried about hardware, and we're not worried about cost of the cloud. All we're worried about is getting high fidelity products that see undercover. But I'm not a resistivity expert per se.
Okay, thank you.
Any more? Yes, please.
Jeff, can you hear me?
Yes, I can very well.
Yeah, this is Alok from IT Bombay. I just got a question about machine learning. You've been incorporating machine learning in your workflows. One problem is that it's all very, very strongly training data dependent. So if I dial up an inversion model, for example, using some kind of training data coming from Australia, where we've got very well explored and drilled deposits. Now, how do I translate it over a green fields area back in India, where the geology might be different, the mineralization would be different? So have you been doing some kind of cross-domain training tests and seeing how your algorithms work?
Yes, again, another really, really good question. So, you know, there's always, for machine learning and AI-based approaches, the training models never have enough input data. To give you an idea, what we do in the geophysics component is, say, for example, we have the Cannington mine. It's a fold, right? Oh, it's a fold. It's been refolded. We run Cauchy over that, and we run it on the magnetics or an RTP. But then what we do is then we rotate the model in different directions. So each mine has thousands and thousands of Cauchy solutions. So in essence, we're dealing with a variation in geometry, rock property, and where you are, for example, if you're near the equator or not near the equator. So in that sense, our training models are significant because we're forward modeling the geology. The same thing, for example, creating synthetic data becomes an important aspect in other disciplines. So, for example, one of the data sets we use hyperspectral data quite often, and it's used in the training as well. So the more and more the geophysics you stack up in the correct Z field, the greater your product. What the challenge really is when you're running your machine learning, that you put your data in real Z space. So when your drill data goes down, it's actually touching geophysics that's relatively accurate for its depth. When you switch in things like micro-earthquake data and signatures of faults and feature extraction around folds and faults, you can train mixed data sets, the multimodal-based approaches, quite easily. But generally speaking, we're not getting enough sample data into the training models. So you need to use forward modeling, for example, in geophysics, to advance that.
Okay, thank you. I think we'll continue this over email because there's a shortage of time, I understand. So thank you, Jeff.
Thank you.
Thank you, Mr. Jeff, for having a wonderful presentation. One thing, what I mean to say, we do have a hackathon in GSI, and right now in every region we are going to, we had already taken the AI ML based projects. From central region, we do have planned and already submitted one project at Chamoshi, the Thanewasna, the known copper investigation which has been handed over. What I mean to say, what Dr. Jeff has proposed, when combined with joint stochastic inversion and structural constraints, the depth sections form a high fidelity input to common earth models and AI assisted targeting. I think the projects which we are taking in the part of GSI, the AI driven for mineral potential targets, I think the methodology which he had proposed, if not, we can think on that lines. Thank you. We'll move to the next presentation.
Thank you very much.
Thank you, Dr. Jeff, for that groundbreaking presentation on AI-driven geophysical modeling. Your insights have clearly shown how data-centric approaches are reshaping mineral exploration for greater precision and sustainability. We now turn to another critical frontier in geophysics, the integration of advanced imaging techniques with petrophysical understanding.
It's my honor to introduce our next distinguished speaker, Professor Shali Vahan, Director of Indian Institute of Petroleum and Energy, Visakhapatnam, and a pioneering force in Indian geophysics community. Professor Shali Vahan has over 20 years of contributions in geophysical modeling, including nonlinear inversion, swarm intelligence, 4D magnetotellurics, and deep crustal studies. His leadership at IIT ISM Dhanbad and innovations using particle swarm and gray wolf optimization have set new benchmarks in subsurface imaging.
Today, he'll speak on integrating 3D magnetotelluric imaging with petrophysical studies for deep concealed deposits, offering a compelling view of how multidisciplinary approaches are reshaping deep exploration. Please join me in welcoming Professor Shali Vahan to the stage. Please. Oh yeah, 30 minutes, sir.
Good afternoon. I'm honored to speak before this important gathering which is hosted by Geological Survey of India, which is the body, which is the backbone of Indian scientific knowledge sharing for the last 175 years. And thanks for having such a generous introduction of mine. But if you really want to know the biodata of a teacher, talk to his PhD scholar, they will tell you a lot of spicy stories. Don't believe what they have said about me. So the other day, in the inaugural, DG was talking about three-dimensional and the deep concealed deposits. So I'll be talking about the three-dimensional, the deep concealed deposits, and I'll be using a surface data and a subsurface data in different form, not airborne data. So I'll be talking about, and I try to integrate how does the 3D MT imaging and petrophysical characterization can really talk about a new exploration strategy. Yeah. So this is the area which I'll be talking about it. Yes. Yeah, this is the profile I took. And this was a profile which was taken after doing a deep, long period MT measurements. It was a long transect, I think about 250 kilometers. So we identified some regions which were showing some conducting heterogeneity at the shallow surface. So we wanted to look into that. And each site that time was acquired for a day. Each site was acquired for a day. After identifying, this was a profile which was taken. This is a profile which was taken, and there were two boreholes. One was very close to the site, and the other was this borehole. And also what we have, and the data spacing was about 1 kilometer. And also what we did was, to see the shallow features, we also carried out ERT survey very close to the site. So what we did that we use an Phoenix MT equipment, and we acquired the 5-component EX, EY, HX, Y, SZ, and this profile was about 15-20 kilometers, and average spacing was about 1 kilometer. And as I was looking for a shallower part, so I was doing, the acquisition time was about 6 hours. One thing I'll try to tell that before we go for a field, we also try to do a forward problem, really to see that by using that to optimize the acquisition parameters, that by really doing that, can I really see the features which I'm really interested for? And then it was boiled down to this. So before I go to the inversion results, I'll try to talk about some of the things which one has to do it. So we look for a small scatter, a low scatter, because scatter talks about the bias in the data. And also we try to look for the error bars, which should be as small as possible, which basically talks about the precision of the estimates. Once you acquire data, so any data you know is affected by both the incoherent and the coherent noise. So overcome the incoherent noise, remote reference MT measurements are carried out 2 magnitude measurements at the same instant of time at 2 different places. In our case, the remote reference site was about 150 kilometers away, 250 kilometers away. And the coherent noise was taken care by the robust processing, which basically tries to take care of the outliers. But the problem with the robust processing was that it was unable to improve a signal quality in the dead band, where the signal is itself very low and the noise is very high, or noise fluctuates as well. Sorry, signal fluctuates as well. So for that, we carried out extra hybrid approach, which was basically combining the weights of coherence weighted estimate and the inverse row variance. So we were trying to take care of that, and that improved the data quality also in the dead band. Yes, another thing what one needs to take care of is that as you have an impedance, from impedance you translate to the amplitude and the phase part. So it's important to look both amplitude and phase part, because amplitude and phase has a Hilbert transform pair. So if I just look at amplitude and try to do it, and if it doesn't follow a Hilbert transform pair, then it doesn't make a sense. It's basically a noisy data set. So these things were carried out. So the next thing was that this observed data, if you try to see, observed data was basically talking about a couple of things. One thing it was talking about, there is a conducting heterogeneity. Also, there is a resistive heterogeneity side by side. So basically, the data looks to be having a conductor, register, a conductor, and a register. That was the data which was showing. So after doing that part, so the next thing which comes is a very important thing which comes is the dimensionality and strike analysis. So if it's a 1D data, go for 1D. If 2D, go for 2D. Or 3D, go for 3D. In fact, Jeff was also talking about that if he has taken a gridding for 2D on a 3D data set, so basically he was losing information. So here also what happens, if one tries to do 2D inversion on a 3D data sets, the problem arises that overestimate of depth and underestimation of resistivity is there. And also, off-profile structures may be spurious, so one needs to look at that part as well. No, this is not the okay. So basically, I don't know, you can just ignore the equations. So we tried to look at the dimensionality part, looking at different parameters, shift skew, Walt rotational variance, the ellipticity, and the skew angle. What these all 4 talked about was basically it's a 3D data set, so you need to carry out a 3D inversion. It's as simple as that. And generally what one should do is that one should try to do a dimensionality analysis using different ways, the way we have tried to do it. Now, once you carry out an inversion, what are the ways to? So we did a mod EM 3D inversion. So it is computationally intensive. So it took a lot of time and large memory setup. And we use CDAC Pune facility to do the modeling of our data sets. So basically 1 hour was trying to take about 4 hours, 1 iteration, and we had typically of 100 iterations or so. Now, before you really go into the inversion, so there are a couple of things I'll try to mention. One should have it. One of the important things is the mesh size. So how close the mesh size should be? What should the minimum mesh size up to what depth, I mean, and what should the maximum depth one can go for it? It also, there is also error flow scheme and the values. It talks about that how error in a data is translated in an inversion. That has to be taken care. Trade-off parameter, which talks about how smoothly the data translates, and also the initially half space. Basically, in a simpler word, if I want to reach to, say, GSI Training Center, from wherever I start, I should be able to reach. It should not happen that if I start from Injera, I reach here, but if I start from somewhere else, I do not reach. So you should have half space also optimization to be done. And yes, the other day we were talking about that RMS is not the sole criteria. So what we try to do it is, when we try to do the inversion, what we got that if you try to see, we are trying to get conductor, register, that it was reflecting in the data set. Also, if you try to see, you are getting a C1 conductor and a register, conductor below the register. Also, this is very close to a borehole, so you are getting this conductor and a register again. So this was the data set up to 4 kilometers, the inversion results up to 4 kilometers. We still try to zoom and try to see it, and what we see that at a very shallow depth, you are getting a conductor, which is all along the profile. And also, there is a register over C1 and C2 is this. So we wanted to look at, basically the smaller, shallower part, and we carried out an ERT survey in that part. And what we see interestingly is that yes, this is empty section, the results which is talking about. Yes, ERT also talks about it, the shallower part, but bit deeper, you are not able to see the heterogeneities which is mapped by the ERT and which is not seen in this. This is basically a typical resolution problem of the magnetal risk. Then what we did was, this was the data available, core data was available, and what was available was basically accessibility data, density data, and chargery data was available. We just tried to plot these. A litholog was also available, and from our resistivity inversion, we tried to take the resistivity values and try to see. And what we try to see that at 150 meters above, there is a low magnetic accessibility and a high chargeability, this region. So we'll try to look into this, and this also help you in making a constraint inversion. Yes. Now, I was talking about the off-profile structures, and if you try to see, there is a register here, but if you try to see C2 and C1, there are off-profile, not on the profile, they're off the profile, and you try to see the C2, it starts developing at around 130 meters, which goes, C2, which goes up to 350 meters or so, whereas C1 develops at a deeper depth, about 300 meters, and goes up to your 600 meters or so. So there is a presence of an off-profile structure. Now, the question is how reliable the model is, how final is the final model. The way we were discussing with other day with Pradeep Singh sir, what to do for this, the reliability structure. So the first thing is, when you do an inversion, the first thing what we look for is that am I getting a real good match? But here what happened was, at the lower frequency, I was not getting a good match. So is the inversion correct? Or what was reflecting to this larger mismatch? And what we saw, that yes, this mismatch is pretty large, and we wanted to see what was this happening, and we tried to do a forward problem for that. And what we did, we tried to have a conductor, and we tried to keep a conductor with a resistivity contrast of 1:10 and 1:1000. And what was seen that this larger mismatch in the phase data was apparently due to a large resistivity contrast. And if you try to see, my data, raw data, the process data was talking about conductor resistor. So that is which is reflecting to the large mismatch in the phase data. Now, the thing is that you get some important features. How do we really go and see those important features? What to do for these important features? So basically what is done is that, suppose I get a conductor, I replace a conductor by a resistor. And what I do is, and also I do with the dimensions, suppose I get, let us say I get by 300 by 300 meters, I make it a 3 kilometer by 3 kilometer. And what I do now, I try to look at the RMS. And what happens that, suppose by changing the conductor, taking a conductor to a resistor, RMS worsens, say from 2.3 goes to say 5.5. And what does it mean? It means that that feature is required for you. So that's a reliable feature for you. If RMS improves, then that feature is not to be trusted. So the bottom line is, try to replace a resistor with a conductor or conductor with a resistor and try to see how does an RMS plays a role. Next thing we talked about was an off-profile structure. Is it trustworthy? Is it trustworthy? So again, what was done that the conductor C1, C2 were replaced by a resistor of say 500 ohm meters or so, and again what was seen that the RMS deteriorated. If it deteriorated means that that's the structure which is required, and so that's a reliable structure what you get it. Now, so this was, I was talking about some important features. So what should we do for the, basically for the, your entire model? So what we tried to do that we wanted to see whether the model is trustworthy or not. So for doing the trustworthy model, we started to look at the phase data. You could look at other data sets also, but the phase data, and we looked for two of the phase, a switch skew and a phase sensitive skew, and what is seen basically that this is an observed one, this is obtained after the modeling. We see there is a fairly good match between these for all the data sets. So it seems that the model itself looks to be pretty acceptable. I told you that in the beginning that we decide the mesh size, and that mesh size depends upon the skin depth, and then that will also define what should the minimum depth and the maximum depth. So in our case, we saw that it was about 11 kilometers. 11 kilometers was the maximum depth what we got it from the skin depth. So now is the question that is my model sensitive up to 11 kilometer? That's one other analysis we tried, because I can get a feature at say 7-8 kilometers, how reliable those features are. So that was one thing which we wanted to do it. And also what happens is that when you take basically Earth is a finite space, so when you take a model, you're trying to take a 10 kilometer basically. So that skin depth also defines that how far we should go away from the model. So that also helps us. So what we tried to do that we took a 1 kilometer thick slab and varied at different depths. We started from very shallow depth, we moved up to 11 kilometers. That is what my initial model was. And what we are trying to see that when we are trying to move, say from 11 kilometers up to say shallow depth, up to 4 kilometers, it was seen that the RMS was again getting worsened. So what does it mean? That the model what we are having can talk up to maximum up to a 4 kilometer or so, not more than that. So now, when this was done, what was carried out was, just a minute. After this, sorry, what we started doing it, that we wanted to look the petrophysical parameters in the sense that some core were available. So we wanted to measure the density, susceptibility, and the chargeability. We wanted to see it, how does it look like. And then what happened was, we tried to plot it on a very famous Henkel plot. And then what we see basically is that when we try to plot it, what we see the data sets are in this region, which is basically talking about low grade of metamorphism, and as the entire data set is in the paramagnetic train, so it is talking about the serpentinization is of low degree. So now what happened was, that there is another famous plot is available, which is basically the combined density susceptibility scatter diagram. And what it does, it tries to take three components, a host rock, a magnetite percentage, and also it tries to talk about the hematite plus sulfide. And we wanted to plot one of the data set which was available to us. And what we see that it is giving us your percentage magnetite is very less, host rock is over 78%, and hematite plus sulfide is 20%. Now it talks about the percentage of hematite plus sulfide. So the problem was we were unable to understand whether it's a hematite dominated or a sulfide dominated. So what we did, we went to go back and saw the chargeability data set, what we had, and we tried to plot on a typical ternary plot, which is basically BGT, the bulk grain and textural plot. And what we try to see it here is that it looks to be that this is a sulfide dominated one. So basically what we talk about is, from this, we talk about a couple of things. We talk about what is the percentage of hematite plus sulfide, then we want to distinguish it. So we use the chargeability data, and we get basically from a disseminated sulfide data set. Then we plot it as a gold bearing of texture and grain properties. It's a region of glow grade stuff. And it indicates, the plot indicates that the region is of low grade subtraction. So just coming to the end, and if I connect the dots, first thing is no data. This should not be done a 2D inversion for a 3D data sets. Sufficient time should be given to see the data initially. Processing takes a considerable amount of time. Processing takes a considerable amount of time. You need to do a reliability check. So before you go trust a model, try to have do some test which can make us confident in talking about it. The spectrophysical data talks about, it can help you in two ways. It can help you in two ways. One way is that it can help you in doing the constraint inversion from the data sets. And also, it can talk about what is basically dominating that part of area. So this, I come to my conclusion, to the last slide. Thanks all of you for giving me a chance to present my work.
Thank you, Dr. Shalivan, for an excellent presentation regarding integration of 3D AMT data and its petrophysical characterization for deep sea concealed deposits. I request from the audience if any query, please. Please. Mic dijiye.
Good afternoon. I am Priyabrata Mukherjee from GSI. So, sir, my question is, during modeling, you were talking about that off-profile structure. So, how much offset is acceptable during the acquisition to take care of this structure?
Okay, no, I'll tell you that I did not went to see the how much offset the acquisition can take part of it. I acquired the data, did the inversion, and I got an off-profile structure. So once I get an off-profile structure, I try to see, is that trustworthy? If it's trustworthy, accept it, else I'll not accept it.
So up to how much offset the structure will come to my inversion model?
Okay, so that I have not seen the thumb rule, but once I got this data, I did this analysis.
And during yesterday's panel discussion, you are talking about to get the coverage of regional empty data.
Yes.
So what should be the spacing and what should be the strategy to acquire this kind of empty data?
Sir, I'll tell you that what I have been doing is that I have been doing a forward problem. Depending upon the geology, I try to do the forward one and optimize the acquisition parameters. I try to optimize the acquisition parameter. That's the strategy which I've been following. And in our case, we had seen that, I think it was 5 kilometer spacing what we had optimized for the entire profile of 250 kilometers.
And my last question, sir. During MT, we are taking some uniform sources from the thunderstorm. But during the acquisition, if thunderstorm happened in that self itself, So in that place, thunderstorm occurring during that acquisition. So how much data will be affected due to that phenomena?
See, what I understand that thunderstorm activities goes across the globe. So it is, I think today in the morning, someone was talking about the lightning.
Yes, yes.
I saw that it is 44 plus minus 5 thunderstorm activities happening every second. So it goes across the globe. Then you have, for the equipment, I'll tell you, yes, for the equipment, we have those filters to protect the equipment. It may happen that the equipment go bad in some frequency range, so that you have to ignore that data set while processing and interpretation.
Okay, thank you so much.
Yes, in the very initial presentation, Mr. Alexander has addressed that issue.
Good afternoon, sir. Thank you for this nice presentation. You told that your reference site was 250 kilometers away from your observation
Yes,
point. So is it important that electromagnetic condition should be same for both your reference site and your observation site?
Very correct, because that has to be there. So I'll tell you that the first remote reference measurement was made way back in late 1970s. So it was, I think, 5 kilometers. Then in Japan, in a coalfield area, they went up to 150 kilometers. We had about 250 kilometers. In Europe, they had about 900 kilometers. Yes, the condition has to be same for the signals to be same. Yes.
Yeah, for removing coherent noise, the electromagnetic condition should be same, I think.
Yeah, that's true, sir.
Okay.
In fact, what you're talking about, we did that analysis to find whether the signals are coherent or not, and then we went for.
Sir, I have a query. Actually, you are talking about the correlation of the petrophysical property with the EMT results. So in a scenario like you have the resistivity value from the core samples of the well data, so it will be correlatable with the resistivity value of empty sections. So we are getting.
Yeah. So I'll tell you that. Yes.
And if it varies, then at what extent it can vary?
See, what we try to do it is that if you see a surface measurement and if you compare with a subsurface measurement, so in subsurface measurement with a lot of kinks,
yes,
right? Where in subsurface measurements are very smooth. So surface measurements is very smooth. So basically surface measurements are an average of the what you get the kinks due to the heterogeneity. So once I invert that, and if I see the average trend from the surface measurement matching with the subsurface, so accept that.
Okay. Actually, sir, at what extent means, just I want to know that you are getting some resistivity value from the MT model. So that will be correlatable, like it will suppose from resistivity MT model, it is coming the resistivity value of 100 ohm meter. Then what will be the resistivity value from this core samples? Like it will be plus minus 10, or it can go up to 200 ohm meter also?
You see, what we do that once we get the data set, when you invert, you know, it's not unique, right? So uncertainty is associated. So we try to find out what is the error associated with each parameter.
Okay.
So we say it's the best probable model.
Okay. Thank you, sir.
That will be the last question.
Thank you, sir, for a wonderful presentation. My name is Avik from Geological Survey of India. Sir, we had a doubt that in our western region, in the Thar Desert area, there are areas which are sand covered, and the thickness of the sand is around up to average of 100 meters, and the groundwater there is highly hypersaline. So whether the MT data will work in those areas if we plan regional as well as local surveys?
Okay, so I'll tell you that there are one more thing to add to that is that also some of the areas we see power line also, right? So what has happened basically that from the power line you have to be far away, and if you try to see the physics, how does an electric field varies with the distance, and how does the magnetic field varies with the distance? One is 1 upon r square, the other is 1 upon r cube. So which is so you have to be far away such that the noise reduces considerably due to the power line, right? And regarding the other part of your question, yes, what basically has to be done, the site preparation has to be done on a very good planning has to be done for the site preparation, in the sense that you need to have a bentonite clay, right? And that porous spot also has, generally what happens that if you try to see, the thermal wave penetrates up to 20-25 centimeter. So generally for our region, we try to go up to 50 centimeter or so, double of it. Okay, so you should try to put porous spot still deep, try to see how far you can go, and then try to have a good bentonite clay. It reduces, not only reduces the contact resistance, okay, it also helps in retaining the same environment for a pretty long time.
Okay, sir, but the groundwater is dispersed throughout the sand and it is saline. So there is no selective location where we can put. The entire area is highly saline because we tried IP resistivity, it failed. So whether MT will work in such situation, that's the question.
No, if see, for shallower part, no. Yes, for deeper part, yes. Shallow part will be getting affected.
Okay, thank you, sir.
So thank you, sir.
Thanks,
thank you for our excellent presentation. No, sir, thank you. We do have time constraint. Thank you. We'll take it later. So we'll move to the next presentation. Thank you, sir.
Thank you, Professor Shalivan, for that illuminating talk on 3D magnetotellurics and petrophysical integration. Continuing our focus on innovation, we now explore how artificial intelligence is transforming mineral exploration. It is my pleasure to introduce Mr. Rajesh Kumar Singh, AI and Innovation Factory Manager at Schlumberger. With over 24 years in the oil and gas sector, Mr. Singh has led the deployment of AI and machine learning and generative AI across a wide range of energy applications, from predictive maintenance to digital oil fields.
He is a graduate in petroleum engineering from IIT ISM Dhanbad and now brings his cutting-edge expertise to mineral exploration. Today, he will speak on mineral prospectivity mapping using machine learning solutions, highlighting how AI is driving faster, smarter, and most cost-efficient discovery. Please join me in welcoming Mr. Rajesh Kumar Singh on the podium.
Am I audible? Yeah. So good afternoon, and thank you very much for inviting us, some person from oil and gas expertise, not from geophysics domain, but we also using the geology and geophysical data, and we see much deeper than what GSI see, like 10,000 meter or below to extract oil. Problem have same, and only thing that context has been changed. So that's where I just thought to start. My name is R.K. Singh, Rajesh Kumar Singh, and I am leading the AI and Innovation Factory business for SLB in not only oil and gas, but across energy. Though my expertise in oil and gas mainly. Actually, I'm really excited to be here to talk about mineral exploration, how we can accelerate. I attended yesterday and today, and believe me, I learned a lot of physics has been involved, and the common aim is to get the mineral faster, right, to fulfill the demand which world is seeing right now. So I will touch another aspect, not going deeper in the physics part because you guys are expert already, but how can we use cutting edge AI, or I would say deep learning or LLM or vector database to accelerate this mineral exploration. So with that, how to next? Oh, okay. Thank you. So I think we have all seen it. I just put this beautiful picture to passing my message that the low-hanging fruits, of course the shallow, obvious deposits, have almost gone. And you all guys know that how we got the first iron ore mines in Bihar, now in Jharkhand. Just very simple native knowledge, and we got it. That's very obvious deposits, right? And now we are moving towards more exploration in the environments of remote location, structurally complex, data-heavy domain. And there's a challenge now, and that challenge brings the opportunity how we leverage the technology to solve the problem and accelerate mineral exploration. So, and I just want to pass this message that next generation of discoveries belongs to those who can see and what other cannot see through data and AI. So before I go and talk about mineral exploration, just give me a couple of minutes quickly introduce what differently we do in SLB and mainly in terms of energy. So we established 7 global innovation factory center. Like you say, I'm mentioning innovation and factory, both things together. Factory means we are not R&D division. We have to implement AI solution. We generally talk about AI on the paper, on the prototype, but the value which we see when it go and we can scale up, that real value come. So that's what we believe, how fast we can bring the innovation on the ground to so that customer or we can get the value. And the next idea that how we do, so we have kind of sometime co-development working together and pinpoint the problem statement, because it's not product, there's no product exists at all for any AI solution. It's always very typical problem statement we solve, and generally we solve together because you have deep knowledge of the area problem statement, which we might not have, but we have expertise in other part of the technology, which we say data and AI technology. And also we also have domain knowledge, but we cannot match with your knowledge because you have the problem statement. And then we accelerate and deploy at scale. So we always start with a small to see quick fail, because we believe things should fast, quick fail, we can learn it. And then once we have acceptable criteria, so we go and deploy at a scale so that you can get you can reap the benefit. So now let me come back. Why do we have urgency of innovation, mineral and exploration? So we all know that there's a demand of critical minerals are increasing thanks to transition, electrification, digitization. They're demanding more critical mineral. However, unfortunately, our discovery rate is very slow. And irony that we have a lot of data than ever before, but we have very fewer insights. And if you see, because we are not R&D, we are all doing business, right? When we see cost is rising, margins are tight, so we are looking solution which can expedite meeting the demand, and there AI comes and can help with you to innovate mineral exploration. And I will come give some example actually later on what I mean to say this part. So before I jumping, I think everybody understood that what could be the limitation, where we stuck actually. So our whole process is very manual, like even today, just before me, they have fantastic solution physics based, but one thing he mentioned, it takes time. And unfortunately, we don't have time because we have to solve the problem, or we have to produce, or as per the Prime Minister vision, anything produced within some 2030, 2040, is not in the next 100 years, right? That time will motivate us. How can we bring the advanced technology, still we preserve the physics and innovate faster. But limited technology is time consuming, involve lot of subjectivity, because many subjectivity and error can come up. And the same time, if you see, you have lot of data coming. If you say geochemical, geophysical, logging, airborne data, many reports, right? Everything there, right? But still, we are not able to discover fast. We can discover, believe me, if I give 100 years, but we don't have that time. In that context, I'm saying we are slow. So here, actually, this is an inflection point. How can this AI really help us? So if you say you have lot of different type of data, some of data is spatial, some are temporal, some are the data in text, I mean reports, unstructured document, field notes. What if we just integrate all those data, bring it in one place? There's a lot of technology available, right? And convert and then convert into big database. There's a technology only. And then we can accelerate, bring the physics and the deep learning method together, so that our prediction probability will improve. It will not 100% accurate, but having some 40% probability to get the mineral, maybe it might give better probability. Okay, you have only 60%, so you have more informed decision, and you know the risk. You know the risk very well when you incorporate everything together. And of course, that will also help you where to drill the bore to get the right kind of data, so that your model improve better. It's not only the processing, even AI can help where to drill. And having fewer wells, getting more quality data that also have less impact on environment. So it all has been connected, and where AI can help. And the thing which has been changing right now, it's moving from, so I will mention here two things which changing everything. One is deep learning. I just say deep learning because of complexity of your data, or messy data, right? And Gen AI, generative AI, all people know ChatGPT, but you can say large language model, and even people now have started working seismic foundation model, so that you don't need to run each individual machine learning model. So this thing is changing, and I will talk how these two main technology like deep learning and LLM can help you to expedite the mineral exploration. And one more thing I just want to mention here, that this is assisted, right? It's not going to displace any human. It's just your very trusted assistant, or you can say advanced digital assistant. Don't take it, it can never surpass the human intelligence. Why? Maybe we can have discussed later on. So when we come deep learning, I put few of the use cases. It's not an exhaustive list. And the use cases that could be prospectivity mapping, feature detection, anomaly detection, data fusion. These are just a few of the use cases which I think we need in today's environment. And the models generally we use, again, it can be more model. I just put the name, like if we have CNN or transformer, any kind of transformer, we can solve the grid, having LSTM, long short-term memory, like solving a time series, like have temporal data, and also CNN for 3D model, for the geochemical logs, everything, you can have multi-layer perceptron. It could be alternative as well, depending upon your problem statement. And the benefit which you have it, you will remove the biasness. Believe me, human is biased always. If it's their baby, it never say my baby is bad or good, right? Biasness, it will remove. Machine doesn't understand what's the biasness. And also, it will keep improving the new data set. It's a continuous learning and can handle different kind of data, like starting from all kind of data, geophysical data, geology, log data, structure report, everything it take care. So And I just put one example. That's something we took from the mineral resources, Tasmania. They have data already published. And if you see left-hand side, we have gravity and magnetic data, and then we did some vertical derivative. We can see a few of the anomaly in even gravity magnetic. Then we club with the geological, radiometry, geochemical, and other data set, and apply deep learning. And then we found some anomaly detection. You can see that machine, of course, we did the testing, validation. I'm not putting the whole process, but the output is that it's very much similar what we are expecting. It's a known, we already know this anomaly here, and that would able to catch. So what we want to show that machine learning or deep learning, whenever we say, there's only one thing I say to everyone, it processes fast and it recognizes the patterns. If there is no patterns, sorry, machine cannot help you. So these are two fundamental principles all AI have been working right now. Need to faster, and where human are behind, because if I give a 1,000-page document, I say I'm going to ask question, be ready in 5 minutes, you will say no, I will need month time, right? And still you might not able to answer. So that capability machine brought it and assist you. So no need to spend a lot of time, and also can identify some hidden patterns which human can maybe omit or say maybe error, but that's something patterns machine can identify, and that's what is a complement to human intelligence to further go ahead and validate the result. Then question comes, what is the role of language intelligence? So we all know that last 175 years I saw GSI, you did a lot of fantastic interpretation study for all the known mineral deposition in India, right? And many consultants have done this report. All those knowledge has been logged in the report actually somehow. Maybe handwritten report, maybe some kind of text. And believe me, it might be somewhere in Almira, nobody even going to refer those things. And based on those knowledge, those consulting study, those detailed years of study, you found the mineral, obvious, somehow successful. How can we bring those data in today so that we use those data artificially extract the thing and having converted into the vector? When I say vector database, believe me, it becomes mathematical everything. It's very easy to search, semantic search, anything. And then you can have your anomaly detection, and you see with my new data set, really it is an anomaly or is following the same similarity search, right? So those type of power that this, not LLM, actually I'm talking vector database, and then you can retrieve. It comes from there. So why don't you use it actually? And then this is something I really is very close to me, the fusion, right? You use all kind of data I mentioned many times, like geophysical, geological, geochemical, remote sensing, other data set, do pre-processing, put the spatial coordinate, whatever, and then you apply the deep learning, train, validate with a known result, and try to find anomaly detection. It's very well-known use case. You can find many difference in the, just Google it, you find many things. But can I fuse with the vector database? And because then in the same way, I also, what, since this is known, and I want to see the anomaly data which are coming, whether it's a close or it's a far away. If it's a far away, it could be maybe geology might be changing or something new mineral, right? And that will provide you opportunity to go in deeper and focus on that part only instead of going everywhere. So that's a thing of fusion. But that fusion can happen at any level. I did here, maybe that fusion can be happen at the data layer itself. That's something depending upon the problem statement, how we are ready today and solve quickly. And definitely if you want to impact, of course it will reduce time, and it provides, I said, geoscientists will get one trusty digital innovation assistant who knows a lot and helping them where to focus and where to deep dive. And also democratize the exploration knowledge. what if we put everything in the database of India? I think US already did. There are a lot of companies involved. They put everything together. It's a knowledge database. And now they are reaping the benefit. And this is real thing coming. I just mentioned one or two discovery. In copper discovery in Zambia, somewhere Africa, a cobalt company claimed that they use AI because it got faster. Just faster. They did not remove the physics, but they did it faster with the AI, which I mentioned. And also some critical minerals in Greenland, right? Under the ice and thick, right? Do you think if you go with the conventional technology, how much time take? Might be 30 years, 40 years, but they did in 2 to 3 years, right? That's the power of technology, but without removing any your physics knowledge. Vision forward, of course, I say that it's augmenting geoscience, means is your assistant, and it's a collaborative with the AI and domain expert. And just think that when you have intelligence system, you are keep acquiring data for airborne or satellite data or coming. It keep updating the model and always up to date. So that's a vision. It's not magic anything. It's happening already. Like you see a lot of example of Australia, or nobody showed any example of US actually. They already been using and they see the value. So that's promising. And some closing thoughts. I spoke a lot, but the thing which I asked to message that rock have not changed for a million years. It's only thing we asked to change the way we want to look at now with the technology. So that the message from here. We have to think, look the rock some different way. And with this, I just want to thank you and happy to take any question. And yeah, thank you very much for your time. And I know everyone hungry. I took a little bit time, but thank you.
Thank you, Mr. Rajesh Kumar Singh, sir, for your illuminating talk on mineral prospectivity mapping using machine learning solutions. As sir is not here, so I'd like to ask if anyone has got any questions, you're free to ask.
Mike, please.
Hello, is it on? Yeah, very interesting presentation. The only problems is how do you use CNNs in prospectivity modeling? From where you get the training data?
So we have already data set available with the where we discovered the mineralite. Those training data set we can use. I put CNN.
Very few,
yeah.
Right? We're like over entire, say, the Rauli belt, you got at the most 40, 50 deposits. Now this area is thousands. It would be, say, 300 by 400 square kilometer. And if you have 1 square kilometer grid cell size, you're looking at millions of pixels. And now training those millions, particularly CNN, where you've got thousands of parameters as you are convolving, how do you estimate the parameters there?
So let me put, yeah, you're right. Putting in this area parameter difficult. What the thing which I want to say that let's start with your known area where you want to see whether this kind of CNN or any transformer, I just put CNN time being because that pretty much everywhere use it, whether it works or not when you're known thing. And with those kind of parameter, at least you have some trust on the ML because people do not trust. And one more thing I did not mention here, bringing the physics together as well because people like use AI informed physics. We also have been using AI informed physics because that give another unknown area where we do not have much or we don't have data outside that range, that where physics help us. That's also research going on. And we also engage in some project. So if your answer is correct, then we have to tweak this whole architecture to come up maybe with a limited data set, physics is still valid, physics not bad, but how can we fuse of physics with the ML model? That's something we can look at.
No, but did you think about unsupervised clustering type of application that's going to work much better? Autoencoders, they're probably going to work much better compared to these supervised models like CNNs.
Yeah, agree, we can try, but only thing, when we say unsupervised, in the business now coming to when anybody funded, when it's unsupervised, people try to hesitate, okay, it's a lot of risky, right?
No,
So
but
you have to bring the balance between both things, right?
It's not about getting money, it's about getting the right solution, isn't it? It's unsupervised clustering is going to give you, without entering the. Now, can you go back to that Tasmania slide that you showed, where you picked up the anomalies?
Yeah, we start. Please, slides. Yeah.
That was very interesting.
Please share the PPT.
Can you?
He's just doing.
Yeah, you showed some anomalies detecting
No,
using
not this one.
gravity and
Yeah,
gravity first
maybe
vertical
in the meanwhile
derivative and magnetic first vertical derivative.
Yeah, I remember maybe they're still setting up. I think they removed the. Yeah. Let me.
Yeah,
let me
this
stop.
one, this one.
Yeah.
So to me, it appears that it's just picking up the blanks where there are no data.
Say it again.
To me, it appears that your anomalies are essentially the areas where there are no data.
Which one you saying? You're saying this part?
Yeah, I mean, yeah, that part corresponds to those blanks in your
Yeah.
gravity data. So essentially, you have got no data there.
No, it's not blank actually. We just this is not blank, which I remembered the data has been provided, but this very obvious we can see something gravity in raw format. So it's not blank actually, what I know.
Okay, I mean.
It's not blank. Maybe we put the color white to just demonstration purpose, but that's not a blank. The
Okay,
blank,
no.
how can I estimate anything?
Okay, I think Dr. Porwal is not satisfied with your answer. Afterwards, you can have discussions during
we can
lunch.
discuss offline.
Yeah, next question, please.
So this is Koteshwar Rao from CMT. So when you are integrating a data, different sets of integrating a data, if there is one of data set having a error, and that will lead to the prediction error. So how can you handle that? If any one of the data set having a error or noise, then by including that, it will create a error in a final prediction. How can you handle that in the model?
No, you're right. If data is erroneous, result will become erroneous. But there's something we, before we put data into any system, we do pre-processing and analysis. It doesn't go directly to data, and error data has been going first stage. And again, when we train the model, validate and train, we'll know what kind of error is coming, and either we have to leave it or we have to further refine or either hyperparameter or remove in the beginning itself. So quality of data important. Erroneous data we generally do not prefer to feed into any kind of model.
Okay.
Last question.
Hello, sir. Good afternoon. My name is Shrikant Singh. I'm from SRK Consultancy. My question is on LLM. How do you take care of, let's say, you are handling a couple of reports or like 10, 15 reports in the same area where people have worked over a period of time, and with time, either there is refinement in the information or there is contradiction from different agencies involved in the project or different ideas from different people, where one report says X, the other report says, no, this should be X or +1 or this should be Y. How do you take care of QCing this data or training your LLM to pick what you should desire in your model?
Yeah, that's a very good question.
Thank you.
And having report and that's what not as per the expectation or that's what you mean to say, right? And should we consider? So I will say that need to, like beginning I said that when we work together and we know if this interpretation wrong or something happened, right? It should not go into the system, because if you go into system and you will get some kind of thing. But one more thing important, even that interpretation went something badly out of the way, when we convert embedment and convert to vector data, right? It might have very low semantic search, right? It might not reflect. So you still have chance that what I'm searching right now and what top K results are coming. So you not to have all those results, you can put the temperature level of parameter you can define, and you might not get after putting filter or some K-top or re-ranking methodology which we can use it. But let's put data there, and only thing it will not appear in your search, or you can see how much similarity you have, what the query have. If very low similarity, of course you're not going to consider, right? So those things we can do while setting the model and initialize any kind of large language model or vector database or during embedding process. So you have those answers. That's why I say no, it's up to you that having just 0.1 similarity, you're not going to take it in your decision.
Okay, thank you.
Thank you.
Thank you, Mr. Singh, for having an innovative talk on AI-driven geophysical modeling. I think what you had asked the audience to use the database of GSI, it is already in EngDR portal. So I think it is open to all. Thank you. Thank you very much.
Thank you.
And summing up today's session, since morning 10, it is almost 13:30. 3 hours we are sitting hearing the presentations. We do have 5 presentations since morning, where 2 were online and 3 were offline. 2 presentations were focused on the new innovative techniques, where mobile MT and the block 6 of NAGMP, utility of the integration of 4 parameters, it was there. 2 presentations were based on the AI-driven geophysical modeling, and one by Dr. Shalivan regarding integration of 3D AMT with petrophysical characterization. So I think all the presentations were excellent, and the audience would have catched the things from that. And I do request GSI, the presence of GSI here, to encash the knowledge which is shared by the presenters in this session. Thank you. Thank you all.
So now it's time to felicitate our distinguished speakers and session chair for their valuable contribution to this session. I invite Sri D.V. Ganveer Sir, Additional Director General, Head of Department, Central Region and National Mission Head to Geological Survey of India, to kindly do the honors. We sincerely thank Dr. Jeff Ketley, CEO of Interpret Geophysics, and Mr. Alexander Prichodko, Expert Geophysics Service Limited, for their insightful and thought-provoking presentations, which have greatly enriched the conference and sparked meaningful discussions. Your expertise is deeply appreciated.
May I now call upon stage Mr. Mahdi Bausaidi, Sander Geophysics Limited, for his talk on multi-parameter surveying under the National Aeromagnetic Mapping Program. Thank you, Mahdi. Professor Shali Bahan, Indian Institute of Petroleum and Energy, for his talk on integrating 3D magnetotelluric imaging and petrophysical studies for deep concealed deposits. Thank you, sir. Mr. Rajesh Kumar Singh, Schlumberger, Mineral Prospectivity Mapping using Machine Learning Solutions.
Finally, I invite Srimati Varsha Ashok Aglave, Additional Director General and HOD Eastern Region GSI, to please come forward and felicitate our session chair, Sri D.V. Kanveer sir, in recognition of his contribution and support to this important session.
Thank you, sir.
Thank you, ma'am.
Ladies and gentlemen, now time to have an important announcement. A national conference on critical mineral exploration and exploitation is going to be held at Jabalpur, Madhya Pradesh in the month of August. To let us know more about this conference, let me welcome on stage Dr. S.R. Basir sir, DDG NMH2, to kindly guide us about this conference. So you're welcome.
Thank you very much. Very good afternoon to all of you. GSI Central Region is going to organize one national conference on critical minerals, their exploration and exploitation on 7th and 8th August 2025 at Jabalpur, the cultural capital of Madhya Pradesh. The critical mineral exploration conference is mainly focused on right from its whole gamut from the exploration activities to exploitation. So in this regard, we have crafted 7 themes. Yeah. 7 themes, right from the critical minerals in the Indian scenario, present status, future prospects, and policy amendments. Second is the geological framework conducive to host critical minerals deposits. Third, the exploration strategies employed for various deposit types. Fourth one is potentiality of critical minerals, analogs from outer space. Next one. Yeah. Fifth one is future strategy and advanced techniques for exploration. Role of AI ML in critical mineral exploration. Sixth is technologies related to exploration of critical minerals. And seventh, the techniques and challenges in recycling critical minerals and identifying substitutes. The main aim of this conference is to provide a comprehensive platform for exchanging ideas, experiences, and strategy to be adopted. So on this platform, I request everybody to come forward and take this opportunity and help for the nation building. Thank you. Thank you very much.
Ladies and gentlemen, we'll now break for lunch. This will be an excellent opportunity to network with your fellow delegates and speakers, discuss the morning's exciting developments, and recharge for our equally stimulating afternoon session. Lunch will be served in the specific locations as it was the previous day.
We'll reconvene at 2:10 p.m. for our afternoon session where we'll continue exploring cutting-edge developments in geophysics. For now, please join me in giving one final round of applause for our morning presenters. Enjoy your lunch. Enjoy your lunch, everyone, and we look forward to welcoming you back shortly. Thank you.
Thank you.
Lunch will be served at the main hall. So you just go outside and you can have the access of lunch. Let me thank all our sponsors once again. We are proud to have Steiger Geosciences and Engineering Private Limited as our event partner. We gratefully acknowledge the support of our platinum sponsors, Critical Mineral Trackers, Data Code, Mining Tech Consultancy Services. Gold sponsors, Mineral Exploration Corporation Limited, Altera Solutions, Geomarine Solutions Private Limited, Hind Metal Exploration Services Limited, Summit Spectrum Private Limited.
We also thank our silver sponsors, Maheshwari Mining Private Limited, United Explorations India Private Limited, Geo Expo, and Sprite Technocon Private Limited.
Welcome to GeoInnovate, Revolutionizing Geophysics, a comprehensive video series exploring cutting-edge methodologies, reshaping the landscape of exploration and resource development strategies. Today, we introduce an extraordinary approach developed by Intrepid Geophysics, the Cauchy method. In situations where standard interpretations yield insufficient structural clarity and target identification from vast historical or new potential field data, the Cauchy method will extract 80% more information from your existing magnetic, gravity, and tensor gravity data. Instead of highly unstable, lacking in dynamic range, and limited usable signal solutions, the Cauchy solutions will provide you high fidelity, low distortion, preserved broad bandwidth signals, and increased sensitivity for anomaly detection. From traditional Fourier and Hamming approaches, high-order derivatives lose information and clarity. With Cauchy, more spectral power is preserved and higher-order derivatives can successfully display more information. And the results have higher fidelity and stable higher-order derivatives. Stable high-order derivatives expose intricate subsurface features while accurately estimating depths, source geometry, and dimensions. Grid and line datasets become fertile ground for stable, high-fidelity downwards continuation, yielding unparalleled depth and structural insights. The method's outputs speak volumes of its reliability and efficacy, exhibiting seamless correlations with other established geophysical techniques such as 2.5D airborne electromagnetics. Rigorously tested against known geological formations, the Cauchy method showcases undeniable accuracy and fidelity. With its high-fidelity processing, the Cauchy method provides clearer images of subsurface structures, leading to a more accurate interpretation of geological features. Enhanced property contrast, such as susceptibility and density, enriches the understanding of subsurface variations. GeoInnovate, revolutionizing geophysics. Discover deep-seated resources with the power of Cauchy mathematics.
Today, reliable exploration data is crucial for making the right decisions. That is why Bell Geospace equipped full tensor gravity gradiometry and magnetic survey technology on the Basler BT67 for optimal airborne data acquisition in energy and mineral exploration. Bell Geo's BT67 comes equipped with the highest resolution FTG system, capable of accurately detecting gravity anomalies with sample intervals from 55 to 60 meters. With magnetics on board, the ultimate G822A cesium magnetometer high sampling rate allows detection of magnetic flux at less than 3 nanotesla over an extended range of 20,000 to 100,000 nanoteslas. All aircraft come equipped with gravimeters for longer wavelengths and deeper targets. For example, the GTZ gravimeter is capable of detecting less than 1 milligal of gravitational field within multiple scenarios. In addition, when required on occasion, the aircraft can carry a LiDAR system that tracks terrain ruggedness with accuracies of 15 centimeters in the Z-axis. So, what makes the BT67 the most accurate acquisition solution for airborne full-tensor gravity gradiometry and magnetic surveying? The BT67 showcases the highest daily production rate with long-range fuel tanks to maximize production. The BT67 also possesses an exceptionally stable platform with 100 foot of wingspan and reduced turbulences technology. The BT67 operates with a twin Pratt & Whitney turbine engine, with 5-bladed Hartzell propellers to reduce systemic noise and ensure smoother operations. The BT67 also reduces passing noises with an overwing upward-facing exhaust. With impeccable maintenance and unblemished safety records, you'll have peace of mind knowing the job will get done as efficiently and securely as possible. Founded in 1994, Bell Geospace are the longest established provider of high-resolution gravity gradiometry data, acquiring FTG in 1996 and utilizing FTG aboard the Basler BT67 since 2007. Bell Geo is equipped and determined to deliver high-resolution, highly reliable data to your next minerals, energy, or geothermal exploration project. Bell Geo is determined to help solve your next geological problem. Give that next exploration a thought at www.bellgeo.com/contact-us.
The company's fleet includes aircraft equipped with unique systems that allow it to perform surveys even in hard-to-reach environments with high accuracy and low noise levels.
If targeting ore-bearing belts, sedimentary basins, basement under platform cover, or suture zones by a deep earth airborne geophysical approach as offered by Excalibur, to 500 meter or 1000 meter penetration depths, it can be expected a doubling, respectively multiple increase of known ore.
Airborne geophysics is an essential tool for junior exploration companies or for mineral exploration in general, because it allows you to cover big areas of ground and boil them down to the most prospective areas. So for example, when we first came into Kazakhstan, we staked 3,500 square kilometers of mineral license. From an airborne geophysics survey, we reduced an area on our Alamus project to a prospective zone, and we recently announced a world-class intercept of 547 meters at 0.7 copper equivalent. A major part of that was due to the airborne geophysics we did initially. With exploration, it's essential you start it now, because the mines that are found today will be in production in 10 to 15 years and generating revenue for the company.
drilling operation is being carried out by Geological Survey of India, Unit 10T HY 06010 at Rajagullapalli Block, District Chittoor, Andhra Pradesh.
Sri Vikram KY Critical Mineral Trackers. A huge round of applause, ladies and gentlemen, for Sri Vikram KY.
The next commodities are manganese, graphite, REE, cobalt and associated mineralization, and it has been allocated to Mrs. Critical Mineral Trackers CMT. Mr. S. Uma Maheshwar Rao, Director Exploration, is requested to kindly come up on stage. RMT for manganese, graphite, tungsten, cobalt, REE and associated critical minerals in part of Alluri Sitaramma Raju district, Andhra Pradesh.
Now, for one more presentation on a very important topic, which is smart technologies for mine safety and fleet management. May I request Sri Vikram KY, Director CMT, GSC Technology Research Park, Indian Institute of Technology, Hyderabad, to please come forward.
Very good morning to the dignitaries on the dais, allied personalities who are there here, scientists, and who are working alliedly for the mineral industry in the India to uplift. So myself, Mr. Vikram KY, I am a director, CMT Critical Mineral Trackers, Geo Solution Center. Today I am going to address a topic on mining safety, current smart technologies for a better mining safety and fleet management system using artificial intelligence.
माइक्रोन मैक कर रहे हैं।
The geological
Beneath us lies an abundance of resources that holds the key to a future with sustainable energy, advanced technologies, and unprecedented growth. Yet, the world is struggling to meet the demands of the energy transition. We need 500% more minerals to power its key elements.
All
such
of
as
you are
electric
requested
vehicles,
to please reassemble to the
infrastructure
conference
for
hall.
solar
We are
and
going
wind
to
power.
start the afternoon session shortly. Please come back to the conference hall and sit back. We are going to start our afternoon session in a short while.
As we did in the last 120 years. On top of this, we need an estimated 41 new nickel mines, 30 new lithium mines, and 21 new cobalt mines. This shift toward a cleaner energy mix cannot happen unless we locate the minerals required more rapidly than ever before in human history. This is no easy feat. With current state-of-the-art technologies, 90% of the drills in the mining industry are in the wrong place, making exploration extremely inefficient. Even with vast financial capabilities, it takes at least 8 to 10 years to discover and mine a deposit. One key reason for this inefficiency can be attributed to low-resolution exploration. The standard exploration workflow involves collecting low-resolution geophysical data, often by hand, to identify drill targets. The challenge is that these datasets provide very limited information and are therefore not actionable. As a result, explorers are forced to use drills as an exploration tool. This is unimaginably expensive, slow, and detrimental to the environment. How do we then tap into the potential of our nations to elevate the quality of life for our people? At Atom Ionics, we are solving this challenge by mapping the layers of the subsurface to understand and effectively manage the abundance of resources under us. Gravio, our quantum sensor, acquires all the geological information there is and supercharges it with Oreo, our AI platform, to create a 3D image of the underground. We not only map out the layers, but also the details within each layer. Gravio can be deployed on drones for collection of continuous gravity data over large regions. The existence of subsurface features has a direct impact on the gravitational field. For example, an ore body that is denser than the host rock will show up as a gravity high, and a water reservoir will show up as a gravity low. Gravio's continuous gravity data acquisition ensures that all geological information is captured. This is done along multiple parallel lines to cover the area of interest. These lines are then gridded together to create a 2D gravity map of the region to identify anomalies.
All of you are please requested to come to the auditorium hall immediately because we are going to start our afternoon session shortly. In next couple of minutes, we are going to start our afternoon session.
With low-resolution datasets, there is uncertainty introduced into these 3D models. But Gravio's high-resolution data reduces ambiguity due to the additional data points being used as a regularization. Density-inverted models typically require the subjective interpretation of experienced geologists. But we turn this art into science by having Oreo, our AI geologist, to interpret these models and characterize geological features of interest. The gravity data collected can be processed
Distinguished
differently.
guests, delegates and participants, please all are requested to please collect in the hall. We are about to begin our technical session.
Last year, we successfully completed the world's largest quantum gravimetry survey in the outbacks of Australia, covering over 200 square kilometers. Concurrently, we miniaturized another system and took it to the other side of the world in the US. These deployments allowed us to prove our system's capabilities in a variety of environments around the world. As we scale, Atom Ionics has forged partnerships with industry leaders across the globe, including DSO in Singapore, Bridgeport in Australia, and Rio Tinto in the US. Countries with abundant resources are seeking a competitive
Ladies
edge.
and gentlemen,
And
a very
we-
warm welcome back. We hope you had a refreshing lunch and took the opportunity to network and engage with fellow delegates. We are delighted to have you reassemble for the continuation of Day 2 of the Next Gen Geophysics 2025 conference. The afternoon session promises to be equally insightful, featuring distinguished speakers who will share their expertise on cutting-edge geophysical technologies and innovations driving mineral exploration forward.
Ladies and gentlemen, to begin the proceedings in our afternoon session, it's our honor to invite the session chair for afternoon session, Dr. L.P. Singh, Deputy Director General, State Unit, Telangana. He has got He has got 3.5 decades of experience in the various domains of geoscience. He was a core member in ISRO GSI Collaborative Natural Project on geomorphological and lineament mapping of the country. His doctoral work on evolution of lower Gangetic plains is a pioneering work. Dr. Singh played a pivotal role in initiating the collaboration of GSI, NRSC, and ITC Netherlands research program on landside risk assessment. Please join me in welcoming Dr. L.P. Singh, sir.
It's my pleasure to introduce Mr. Karunakar Gandarapu, a geophysicist with over 35 years of experience in mineral and oil and gas exploration. He has worked with Geological Survey of India and Vedanta Hindustan Zinc and holds a gold medal in geophysics from Andhra University.
Mr. Karunakar has pioneered drone-based and heliborne surveys and will speak on advancing mineral exploration with cutting-edge geophysical surveys. Please join me in welcoming Mr. G. Karunakar on stage.
Respected Dr. L.P. Singh Saab, DG Saab, all other dignitaries, students and all, good afternoon to all of you. So I'm going to speak on two recent new technologies. One is UAV-based magnetic surveys, and the other one is deep IP resistivity surveys, which use multi-channel full waveform transmitter and receiver recording and different layouts. So at present, the geophysical advancements over the last decade, it is happening on four important factors. One is the instrumentation. So the resolution is increasing and the sensitivity is increasing, and the development of number of sensors. Previously we used to work with one or two sensors, now multi-sensors, multi-channels, like that instrumentation is developing. And the acquisition procedures, techniques, they're also changing. And they use all multi-channels, multi-sensors, and using of drones for the aerial surveys, and use of borehole tools in the borehole, and the data processing techniques, which are because of the huge data we are collecting. So the handling of the data, data management, processing, interpretation, 3D modeling, inversions, all those joint inversions, all those things are improving. And last but not least, that data integration, that is very important, as for the any kind of a success, it requires data integration, proper data integration and interpretation using AI and ML tools and high quality target generation for the drilling. So first I will speak on the UAV based magnetic surveys. Of course, we all know that the magnetic surveys base is the Earth's magnetic field, its own Earth's magnetic field, and which is giving us any of these magnetite rich rocks, which are giving us a secondary magnetic fields which are detecting. And with this detection, not only metallic minerals and the determination of the trends, any other faults, extent, and the geometries of the magnetic bodies which are being derived, so that this information is being interpreted in terms of geology. For a geologist, the magnetic method is a very fantastic tool to have a more of a helping for this interpretation. So now if you see that there are variety of magnetic sensors available in the market, that is a flux gate magnetometer, which is a vector type, like you can measure all three components, and the proton precision magnetometer, which is widely used in the ground surveys, which are total field measurements, And the overuser magnetometer, which is much sensitive than the proton precision magnetometer, which also used widely in the land-based systems. And most of the airborne surveys are being done by optically pumped magnetometers, cesium vapor, or rubidium or potassium kind of sensors. So the multiple sensors, if you use, you can measure horizontal and vertical gradients. So there are many makers like Geometrics, Zintrex, GEM Systems, and GeoDevice, like that. And coming to the drone surveys, the most of the drone sensors used are I listed below with their make of the sensor and the what frequency it records. So the GEM Systems Canada, they have a potassium vapor magnetometer which records 20 Hz samples, total field measurement. And the Geometrics USA, they use the mag arrow. They use cesium vapor sensor, total field measurement, and 1000 Hz. And the GeoDevice Russia, they make cesium vapor magnetometers and overuser, and which are 100 Hz and 5 Hz. Overuser also used by GeoDevice. And Sensis Germany, they make fluxigate magnetometers, which are 200 Hz, 3 components of measure. And SPH Engineering Latvia is marketing Q-spin, that is Mag Nimbus, which is based on the pulsed laser pumped rubidium, 3 components at 1000 Hz. That is the latest development is by the Q-spin. So overall, if you see, the mainly the mineral exploration that is used by GEM Systems, Geometrics, or GeoDevice, whereas the Sensis and the SPH Engineering, that sensors are being used for the near surface or UXO type exploration. So at present, we are using, I'm from Steiger Geoscience, we are using the mag arrow as the Geometrics sensor, which is highly sensitive, and 1000 samples per second, which is being recording. And we use the carrier drone is DJI M350 RTK drone, which gives a very smooth operations, and carrying capacity is around 2 to 3 kilo, whereas the mag arrow is only 1.2 kilogram if you add the battery. So the maximum speed we use for these magnetic surveys are around 10 to 12 meters per second, and the flying the endurance of the drone is around 55 minutes, but we use around half an hour to 40 minutes only. It means every time we have to change the battery and send again. So multiple times we are using the drone. So every 1 hour or so we are changing the battery so that we get the maximum output. So we collect about 150 kilometers in a day if the day is good without winds. So that and the positioning of the drone is very accurate. They use the GNSS support or RTK support. And the mag arrow, which is having a very less heading error, which is less than 5 nanotesla over entire 360-degree spins. And we can download the data every time through Wi-Fi, and the sensitivity is very high. So before doing the magnetic survey, we have to go for a topographic information. We have to collect the topographic information. So we use either photogrammetry or the LIDAR survey. So which is the sensors is shown there. Like photogrammetry means only the camera we are recording with 2 different angles. So ortho photos we are taking and then estimating the topography. Or if they use a laser technology, then laser directly we are getting all the laser return signals. So we are measuring the DSM and DTM. So we can use same drone. Currently we are using same drone for the topographic survey also, so that we get the accurate topography so that we can plan magnetic survey to follow the terrain. So this is the thing which I think a pre-requirement of the magnetic survey is to get the high quality terrain data and then plan using the mission planning using UGCS. We are using UGCS software to plan with the heights, whatever we collect. So it will follow the terrain. If you see that, LIDAR survey will give us a digital surface model, which includes the trees and buildings or any towers, everything is covered. And we strip it out, de-strip the vegetation and all the physical features to get the digital terrain model, DTM. And over the DTM, we plan, we at a constant height. Suppose if it is 30 meters or 35 meters, we decide on the height of the trees or height of the buildings and whatever physical features on the surface. So once we decide the height, then same height will be maintained and survey will be conducted. So some of the ground control points we have to take using DGPS in order to have a better positioning. So we do take a lot of ground control points on the blocks. And the another factor of quality is like sensor, that drone sensor has to be kept away from the drone so that the drone related noise, engine noise or propeller noise, those are the high frequency noise which will be disturbing the data. So that is how we keep the sensor around 3 to 4 meters away from the drone by ropes. So the ropes also being supplied by the geometric, so we use the ropes to put it down so that we get the good quality data. And also there is another factor is like wind or anything, like the sensor rotation, swings, vibrations, all those things also create some low frequency noises. So that is all based on the skill of the operator, where how you will tie the ropes, how you will handle those drone to go smoothly. So that skill is important here to maintain those kind of rotation swings or pendulum motions and all. So we are doing best to arrest those other kind of noises. So we have a good suspension system so that the noises are minimized. And of course, the drone operator skill is very important here. So if you see that one figure, that if you're keeping close to the drone, then you're getting additional noise from the propeller or engine or drone itself. So that I think keeping it 3 to 4 meters away, so we are reducing that drone noises. So if you plan any drone survey, so I told you that we have to know exactly the topography. If you don't know, then if you send the drone flat and it is going to hit the object which is above whatever we have planned. So generally we do planning using this mission planning, UGCS, after getting all these LIDAR or photogrammetric survey. So all these topographic information is fed and height is fixed. So terrain follow will be there for the drone. So whatever the endurance is there, like half an hour is the flying time. So we give the lines, we fed the lines information to the drone, so that only pilot requirement is to send it up and then leave it on autopilot. So it will go and do the survey and come back. So this kind of, and also if you want to have a more refined way of terrain follow, you need to give more of a waypoints into the drone. So if you give more waypoints, then the drone will be disturbing, like it going up and down. So it will also create some noise. So generally we smooth out for a 10 meter or so, 5 to 10 meters, we smooth out depending on the terrain, so that drone will be smoothly going up. So over a big area, suppose we got about 50 square kilometer area, this is about 50 square kilometer area, then so we have to make it into parts, because the drone radio communication is only around 2 kilometers. 2 kilometer radius, we can see the drone where it is and how it is functioning. But beyond 2 kilometers, we will lose the radio communication and we will not be able to see. So we don't allow that. So for that, we have to make the blocks into sub-blocks and fly from there to avoid that missing of the radio communication. So those spots are like doing the survey from different sub-blocks and then joining together. So this is also a skill required to exactly go into the same line, and with an overlap. We do overlap about 50 to 100 meters if there are two sub-blocks are coming up. So 50 to 100 meters overlap, we do that. And this is the first product which you can see on any of the drone survey. So after doing all these reductions, you can see the total magnetic field maps, which is really good. So I have worked extensively on the ground, and now for the last couple of years we are working on the drone, and the data quality, if I compare, though the amplitudes are less, because you are going height, your cube of a distance, your signal strength is reducing. But the systematic way of taking up the lines gives us, even the small anomaly also will be giving a continuity, and we are able to see a lot of structural information. So for gold and copper, we worked several projects, and we got very good structural information. Every client is very happy with this information. One such project we have done in India is the mafic, ultra-mafic complex. I'm not giving any area because of I work for clients, so I cannot show their maps till they gave the permission. But this is one mafic, ultra-mafic complex where the nickel, chromium and other PGA elements area, where the first product TMI has given a lot of information, and the RTP and the RTP band pass, it is giving clear structural, very good structural information, and it is well correlated with the known geology. And more of the interpretation can be done by the geologist. It is quite helpful for the geologist. And this is one gold area where we have done both the LIDAR topography on the this side, and the drone RTP. You see a lot of trends are being picked up. Even the survey is at around 35 to 40 meter height. So we got very good, excellent data to make interpretations easier. And there's one manganese project we have done. Of course, manganese is not directly detectable through this, but there's an association with the magnetite or some iron. So we are trying to follow the trends or some of these breaks. So, and from the known, how the signatures are tallying, so we can go to the unknown. So there are some number one target on this side, left side is a known place where the 2 and 3, 4 we have interpreted. So similarly, there is another block which is directly associated with the magnetic highs. So it is not a direct method for manganese, but we have to see that how that is associated with the magnetic. So we do also the 3D inversions of the collected magnetic data to see the subsurface how it is, particularly for the magnetite rich bodies. We can model it, and maybe we can estimate some potential resource. Of course, this is not correct to say that estimating resources, but magnetite it is having a relation, so we have that formula to convert the magnetic anomalies into the some type of grading and estimating the resources. And we have several clients in India like Vedanta, Hindustan Zinc. We have done a couple of projects, OMC, Aditya Birla, Deccan Gold, and Jindal. We are working more than 4,500 line kilometers of drone survey we have completed in the mine site areas, in the green fields, in the forests, in the very rugged terrain. So we are doing it, and also in Zambia we have done several projects for the green field areas. So particularly the base metals, gold, a lot of demand coming up for the base metal gold, of course iron ore. So the next topic which I want to speak here is on the deep IP resistivity survey. What are the advancements, I will tell you. So that is a conventional, if you see the left side, that is a conventional method is like maybe 4 dipoles, n is equal to 4. If you use 50 meter dipole spacing, then you are able to see only maybe less than 50 meters only. So, but you can have more number of dipoles, and we can have a different kind of configurations, and you can increase the power, transmitter power, to see more deeper and deeper. So this is the one which we are using currently, current advancement, and also we are doing a lot of projects in India. That is having, our instrument is having more than 20 channels, which is a 24-bit system. And a QA/QC can be done directly in the field. In the field itself, we can see the decay curves. In the field itself, we can see the pseudo sections, so that we can take a decision, okay, this is working or not. So the spread which we use there is 30 dipoles are being used simultaneously, means 50 meters is the dipole interval, dipole spacing. Then 1500 meters spread length, we are able to record a single current injection. Also current injections are being little bit broadened up so that we can see the deep. So 100 meter current dipole and the 50 meter receiver dipoles. 1500 meters we are recording. We are able to see, if it is a dipole, we are able to see 300 meters deep. And if it is a pole dipole, we are seeing 600 meters deep. So those resistivity and chargeability, both are we are being mapping. And the transmitters also, recently we have taken one transmitter, which is an intelligent transmitter, which when depending on the resistance which is there on the ground, so it automatically adjusts. We can leave it on automatic or we can take it on manual control. So which gives a very good transmitting power, which is being, the data collection is very good in this. And also having safety features where if there is anything happens like short circuits or open loop, or any over voltage, it automatically shuts down. And another advantage of the new technology is like full waveform recording. Full waveform time series recording of transmitter, means of the current and also the receiving voltages. With the time we are recording, so that in future any processing new technology comes, they can use that. Currently, whatever available technologies are, we are combining those voltages and currents and measuring these chargeability and resistivities, but still we are recording and giving it to the clients. Full waveform recording is being done from our side. And we are using porous parts which are maintenance free, which are lead chloride porous parts, which are fully sealed, so that those the liquid overflow or liquid filling is not required. So those kind of very sensitive, highly stable porous parts are being used by us. And the layouts, that is also very important. Like general layout is whatever I shown is general layout, which is 50 meter dipole, and you put on a line, 2D line, and collect the data. But there are some configurations available which are double offset. I will show you next slide. Oh, this is IP equipment we use, which is IP receiver is Elrec Terra, which is Iris France, 20 channel, full wave recording, real time monitoring, visualization of decay curves, all channels, pseudo sections, which I told, and inbuilt GPS, connectivity to laptop, smartphone through Wi-Fi. And IP transmitter is TIP 12,000, which is a 12 kilowatt, intelligent functions, and full waveform recording, safety features are inbuilt. And we can give the power through a motor generator, which is 15 or 20 kilowatt. And non-polarizing electrodes, which are using lead chloride, which are porous parts is being used. So that 2D section, which normal survey, the 2D section, which is 1500 meter long spread, which I told, what we do is we don't push. Generally, pushing is there, like once you current injection is there, then the next position is like all the potential electrodes are pushed, and the current electrode will be going ahead. So, but what we do here is like keeping the all 30 dipoles fixed. We are passing through the spread. Means we are current electrodes are behind or ahead. We are recording. It means we are recording both ways. So complete spread is fixed, and our receiver is fixed, and whereas current electrode is moving all through the spread, so that we are mapping in the ahead or behind. So we are getting a very good quality data, and we will be able to see now with the dipole what I have seen the section that is chargeability section is 400 meters we have seen with the dipole with the 1500 meter spread. And this is the one which we have tried and we are trying to do. We have not yet started in India, but the 3D IP survey with 3 lines, double offset survey. This is called the double offset survey, where there are 3 receiver lines. Maybe it is offsetted by 100 meters or 200 meters, depending on the client requirement. So this kind of survey can be done along the strike. Generally, IP survey is done across the strike, but this kind of 3D survey can be done along the strike, so that we can map in 3D. All these resistivities and chargeabilities we can map in 3D, and also reduce the number of kilometers and fast track, because if you go across, we have to go a lot of distances on both sides. Whereas if you go along the strike, there is no need of excess coverage. So this is being successfully done in Australia and US, Canada. So I will show one case study of US because of not working in this India, but I can show one case study. I think thanks to Terra Resources, which we are associated with Terra Resources Australia, they have done the processing work of this kind of a discovery, which is Antler in Arizona, USA. So in this particular field, already they discovered the polymetallic VMS type deposit. 70,000 tons were mined out up to 150 meters, and they stopped exploration since 1975. But again, the new world resources, they came up in 2020. They want to do resurvey and check is there anything left out at depth or any sideways. So they have done several geophysical investigations, which is first one is the drone magnetic survey with lines spacing 100 meters and 40 meters above ground, and all the lines are 45-degree direction across the strike, and they found anomaly. That is the anomaly which you are seeing, that dotted one, and they found the anomaly, magnetic anomaly, and then they did IP survey over that along strike. You see the lines, double offset lines, 3D IP survey along the strike, which is central line is also a transmitter line. Means that power injections are along the in the central line, and both central line is recording, receiving receiver potential electrodes also there, and the side line 1, line 2, line 3. All 3 lines are being recorded for one single injection on the central line. So that is how you can come back and do on this side also, across the strike also, but you see 3 lines. After 3 lines, you can shift the transmitter line to the leaving the third line, fourth line, and third line becomes first line. Third line becomes first line, second line is the transmitter line, and third line is another receiver. So like that, along strike we can make it. And these are the results from the double offset 3D survey. Chargeability 3D model generated, and these are the slices, depth slices of 100 meters, 200 meters, and 400 meters. So 100, 200, it is clearly visible, and 400, it is dies down the chargeability. And the same way, resistivity, that is also showing anomalous, anomalous means conductive. That is all red is conductive. Resistivity depth slice is also showing the continuity of the particular anomaly. And those are being drilled, and drilling also you can see on the chargeability model, and there are intersections of polymetallic, copper, lead, zinc. So that is the finding is like 500 meters strong chargeable anomaly found and drill tested. And the first hole intersected 22 meters of thick mineralization with 7.8 meters massive to semi-massive sulfides. And currently, after drilling, the resources are around 7.7 million ton, 2.2% copper, 5.3 zinc, lead, silver and gold. So this kind of an integrated approach, I think we can make such findings. That's what my message is. Like to summarize my talk on these two topics. First one is the magnetic survey. Selection of proper drone magnetic sensor is important, which I want to convey is sensor is also important. That's why I shown all the sensors available. For the mineral exploration, use best sensor, and the procedures are, and the survey procedures, like you have to follow, you should get the right topography to plan terrain follow, and use the best pilots to do the stabilized surveys. And in the deep IP resistivity 2D, 3D survey, high power, like more than 10 kilowatt and using more than a kilometer spreads, and 2D, 3D type of work with a full waveform recording and visualizing in the 3D, that is important. So the new advanced technologies will not only help in fast tracking the exploration projects, but also helps in preparing conceptual geological models leading to mineral discoveries. So thank you very much for giving this opportunity.
Thank you, Karnakar ji, for giving an insight into the drone technology as well as the IP resistivity. I'm sure there are many, because since so many months we are talking only about drone technology and various aspects of it. So he has given some glimpses of the sensor dependence on the interpretation or mineral exploration in drone based magnetic survey, as well as some insight into the IP resistivity. So I'm sure there are many questions, many exploration geologists sitting here. So if you have some questions.
Am I audible?
Yeah.
So I have only one simple question. When you are acquiring a data for a traverse of 1.5 kilometer, there will be definitely topographic changes. Are we accommodating these topographic changes wherever we place our sensors when final interpretation of the depth section?
Yes, we are putting into the inversions, like inversion programs. We are using the topography into the inversion for visualizing and doing the inversions, yes.
So for doing inversion, it is fine. When I'm acquiring the data with the electrodes, potential parts, whatever it may be,
yeah,
there are topographic changes. So are we accommodating those changes also in the interpretation stage?
Yeah, we are incorporating, yes. We are
taking this porous spot-wise elevation also during equation.
Yes, yes. We are taking the GPS position with heights also.
With heights also.
Yeah.
Fine. Yeah. Thank you.
Yeah. Any more questions? No one?
Yes, there is
please.
someone.
Sir, my question is, electrodes are fixed and current electrodes are moving, so resolution and coverage of the depth, is it effective, or we will get a high resolution and depth?
Yeah, good question. Actually, putting transmitter close to receivers will give a noise in the very close by electrodes, you know. So that is there, but we take little bit offset, 5 to 10 meters offset from the receiver line. We don't cross the current line onto the receiver line, and also the electrodes are placed 5 to 10 meters away from the receiver line. If you are doing 2D, if you are doing 3D, then of course there are two methods. One is 3 lines, central line also being acquired along with the transmitter current injections on the same central line, or central line is only current injections and the 2 lines which are receivers. If the 2 lines are receivers and central line only the transmitter line, then it is not perfect. there is no offset is required. But when you do a 2D line, there is an offset required. But this gives you current electrodes behind, current electrodes ahead, like two ways you are getting the signals, right? So that helps us in the interpretation. We do the inversions using current electrodes on behind, all current electrodes behind, we do the inversion, all current electrodes ahead also we do, and combinedly also do. So to see, sometimes what happens is because of the dips, the data which is one way if you are seeing, sometimes you may miss. Whereas this way, we are doing both ways. This is an advantage. If you don't require, we can remove. Or whatever we have seen it is best. Any difference is there, we will see in the data.
Okay,
Thank you.
sir, thank you.
Thank you. Now we can invite the next speaker, please.
Thank you, Mr. G. Karunakar, for your insightful talk on advancing mineral exploration with modern geophysical methods. Now, it's my privilege to introduce our final speaker of Day 2, Dr. Subhash Chandra, Chief Scientist at CSIR NGRI and Associate Professor at ACSIR, a leading expert in airborne electromagnetics and near-surface geophysics. Dr. Chandra has pioneered high-resolution aquifer mapping in India and received top national honors, including the National Geosciences Award and election to the National Academy of Sciences, India.
Today he will deliver his talk on unlocking near-surface structures by integrated geophysics, a topic that bridges applied research and practical innovation in near-surface exploration. Please join me in welcoming Dr. Subhash Chandra as he brings the exceptional session to a close with his vast experience and visionary perspective. Over to you,
Please,
sir.
sir.
Thank you very much. Thanks a lot. Good afternoon to all of you. So I'll be presenting on unlocking the near-surface structure by integrated geophysical approach. It's not only integrated geophysics, but integration of all geomorphology, geology, geochemistry. And my presentation will be focusing on different scaling, like from very deep to the very small or near surface and very small feature like fractures. So it is more kind of institutional presentation, but then I'll be also taking to the airborne geophysics and try to see the mineralogical and hydrological aspects. So this is actually, this provides the knowledge from, knowledge and understanding into the structure, composition, dynamics of the earth interior, and it is also useful for economic study, like for mineral and energy resources. We are also into applying the geophysical approach for societal, industrial, and strategic need, like earthquake, groundwater, power plant studies. We are providing a site for where the safe power plant can be established. Even very recently, we have also carried out a couple of projects for tunneling. So how geophysics can be used to generate advanced knowledge of the subsurface where the safe tunneling can be done. So broadly, introducing to about the NGRI, that NGRI's work can be broadly divided into three, where we are dealing with the structure and the dynamics of Earth surface, Earth, earthquake hazard, and then georesources where mineral, hydrocarbon, water. So this we are dealing. We are carrying out the basic and applied research. We have a number of observatories where, like seismological, GPS, magnetic, gravity, geothermal, magnetotelluric, borehole observatory. We have also experimental hydrological park to understand the complexity of the subsurface. And presently we are working on geological hazard assessment, including early warning system in Himalayas. Water security, we are doing a large campaign using heliborne ground-based measurement for sustainable ground resource management. We are also currently focusing on the hydrocarbon, uranium exploration, geothermal. Geothermal is very, I mean, of course we have been working since past, but now current focus is much more on geothermal. And as electronic is very rapidly developing, we require a lot of lithium and RED, so our institute is currently focusing on this. And AI/ML, as we have been listening for the past 2 days, it is a new branch, and how best it can be utilized, and how reliable the interpretation is there. So we are trying to use AI/ML along with the joint inversion using the petrophysical relations. So we have a couple of projects and carrying out to see that how reliable translation can be done. I mean, these are the few examples for if you are looking at large scale features like, you know, up to 100 meter deep. For example, this is from the more than 26,000 P-wave receiver function from 54 stations over the Himalaya, and that provides a 3D information about the Himalayan, I mean the subsurface, how the plate is under plating into the below the Tibetan plate. This is the structure of the Moho at around 40. So in fact, the Moho is found deeping from lower Himalaya towards the upper Himalaya from 45 to 65 kilometer. And MST also can be seen, not very clear signature on the ramp or the slope, but then we can see broadly, and they have a contrast characteristic like low velocity and high velocity. So those features we can very clearly see. This is from the Manitou Tirlik. Before the lunch we have seen a wonderful presentation that how to do the 3D inversion and how to the forward modeling of the MT data, and then see especially about the sensitivity. So this is the data and giving about 10 kilometer structure over the Himalayas, and this is directly linked with the subsurface geological conditions. Certainly, no geophysics is free from the ambiguity. There are a lot of ambiguity. There's a reason why we need a kind of integration and supporting data. But this talks about the resistivity structure of the subsurface of upper 10 kilometer. And this is about the geothermal, like, you know, more you go deeper and deeper, in general resistivity increases, temperature increases, so general resistivity also increases, which we can see here that there is a gradient increasing resistivity. But there are certain anomalous borehole which has increased temperature around more than 40 to 60 degrees centigrade, and we can see also in the MT data there are high, the resistive structure. So, and there are conductive structures. So geophysics works based on the contrast. So if you are getting this kind of resistivity distribution, and we know the broader geology, and then finally we can interpret in terms of those kind of anomalous feature what it talks about. We are also carrying out a lot of work on the seismology, and initially started with the earthquake prediction, which probably is not possible, but then how these knowledge base can be used to have a earthquake-proof building construction so that the loss of life is reduced. And these are the two map, in fact, talking about, what is the hazard. This talks about like what percentage of the building can be affected if you have a earthquake of magnitude 8 or more. So this is from Dehradun and Lucknow city. This has been developed. And this is upcoming work on integrated geophysical, geological, and geochemical work for mineral exploration, where we aim to integrate like airborne geophysics, electrical vector radiativity imaging. Actually, this is a little bit different than the normal ERT, where we take care of the directionality also. In normal radiativity, we take magnitude, but here we are taking directionality also. That's why it is called electrical vector radiativity imaging, which is very, very recent, and we are further developing. And monetarily, gravity, reflection, seismic, geochemistry, and geochronology. So these are the integrated approach we are trying to see for a comprehensive understanding of the mineral deposit in a 3D fashion. We have, more than 2 decades we are engaged for airborne geophysical survey, where primarily electromagnetic and magnetic has been carried out for mineral exploration, starting with the kimberlite with the NMDC, followed by with the AMD for uranium exploration in almost different parts of the country. And very recently, in the year 2012, we have tried to introduce, in fact, the heliborne geophysics in India for hydrogeological applications, and where we have started from 6 pilot area from, in the Jaisalmer, then in the Rauli Hill Ranges, near Dausa, in the Patna, the Ganga Plain, near Nagpur, the basalt, and the Tumkur, Karnataka, for the granitic terrain and coastal aquifer near Kadlur, Tamil Nadu. So, and then followed by, we have in fact extended it at Allahabad for buried Paleo River channel, what talk like Ganga, Yamuna, Saraswati, whether it is Saraswati or not, but then we have discovered a Paleo River. We have also introduced, we have worked for the Surat Smart City for water security, and a large experiment we did it for Central Groundwater Board for arid region, where we have tried to cover 4 lakh square kilometer area in 2 phases, where phase 1 has been completed, and now phase 2 they are going through the tendering. And we have also carried out a couple of projects for tunnel, one from Rishikesh to Karnaprayag, and another across the Western Ghat from Thallassery, Kerala to Mysuru, Karnataka. And yeah, so in geophysics, very important it is that what should be the data density, and this is a schematic diagram showing that what is the role of data density and how our model is there. So suppose these are the 2 different kinds of the dots are there, and as a earth scientist, we try to make like assessment what could be whether it is lineament or some connective feature, and if we, this could be one model, and another person can say that this could be another possible model. And if we increase the data density, then our model is very, very restricted. So by increasing the data density, we are reducing the ambiguity in our interpretation. And this data density, in fact, has to be as per the degree of heterogeneity. So, and then another challenge is that what is the resolution? There are lateral as well as a vertical resolution. So what we have done for used for the mineral exploration, that was a single moment system, whereas for the water we have used a dual movement, because for the water the soil is also equally important as the deep aquifer. And here we are trying to use low moment, high moment, and even early channel, which is even within the on-time data also we are trying to model. So we get the effective data from 4 microsecond. 4 microsecond roughly you can say from 4 meter onward. So again it depends on the conductivity distribution. And if you take the first moment, the low moment data, you have a 4-5 layer within top 50 meter. And if you take the high moment alone, so top 3 layer has been merged into single layer. So we are not able to differentiate between these 3 layers. So and these our top 3 layer is combined into one, and then we are getting it. Once you jointly invert, then we are retaining all vertical feature. So I mean, it is very important beforehand to know that what is our objective and what should be our geophysical tool. So it's not like that everything can be applied everywhere. And of course, this is from the single moment VTEM data. I'll quickly pass because I got a message to conclude fast. This is the, in fact, result from Ganga Plain near Patna. In fact, this is the paleo channel. This is aquifer. This second aquifer. This line passes through the Khagol, in fact, and there is interconnectivity of these two aquifer. And if you slice, actually it is not here, but then we can see that where the paleo channel is interlinked with the second aquifer. This was talked about the arsenic to management, but I'll skip it. This is another actually discovery which has we published in geophysical research later, and near, in fact, this is Allahabad, Prayagraj, and this is a Ganga river. This is Yamuna, and so we had expected that there is a third buried paleo river which should be emerging at Prayagraj, Sangam, but in fact we got a paleo river over here, and so meandering pattern of this paleo river is the same as the Ganga Yamuna. So that means they have suffered a same kind of tectonic shift. And very recently we have extended up to Kanpur. So 200 kilometer buried paleo channel has been discovered here. See, the paleo channel and aquifer, I mean lithologically they are the same. It is a matter of dimensionality. So how linear and how connected. So continuity with the connectivity is one crucial parameter where data density has a big role to play, that whether it's a continuous feature or a localized feature. Otherwise we can't differentiate. So scaling and the data density plays the major role. This is about, I mean, this may be interest, like this is in the Arauli Hill ranges where this is a geological map. In fact, you can see there is a 12 kilometer shift because of the faulting, etc. And there are a lot of folding, faulting, you can see here. And this is a geological, I mean the magnetic map, which again reflect the same thing. And if you see here, it is a ratio T from airborne data, and this is the geological cross section along this line A, and then another line where we have the data, we took it. The tectonic shift can be very clearly seen, not only in the quartzite, even within the alluvial also this tectonic shift can be very clearly seen. And this all what I am talking has been validated by borehole. This is I think last slide. So this is on the Kimberley arm. So these are the granite, gneisses. This is a granite, and these are the schist belt. And there are a lot of ferruginous quartzite, sericite, BIF, etc. And then if you go back, there is no signature of any lineament, but then if you see the magnetic, it has given a number of additional, so these are the boundary of the schist belt, but there are number of features which is giving that there are probably things are shifted and there are linear, probably this could be faulting, etc. But we can't say. And then if you see the radiosity, very clearly this mineralized band can be seen. Within there are disconnectivity. So because the data is at 145 meter spacing, the 2 kilometer is the tie line, 145 meter is the flight line spacing. So very, very high resolution. And then, but then hydrological application, we have tried to get fracture. These are the fracture network. and these we have given a term called hydroline. So this is not based on the resistivity alone. This is basically based on the sensitivity of the geophysical parameter. I have to conclude fast. And in fact, we have also calibrated while drilling the penetration rate. Where more fractures are there, the drilling rate goes much faster, and there only your resistivity is quite low. So we can see very clearly there is a strong correspondence. Even the fracture distribution, and even in fact, rather it is a conductivity distribution with the depth in gneisses and the cyst can be seen very clearly, and that has been modeled here. These are the published, so can be seen in the published literature. I think this will be also important to see, like if you see your eyes here, put in your eye 0 to 10 meter, we are trying to go deeper, and how the dipping structure of the geology can be seen. We can see here it is the conductivity is progressing towards north, further down 70, 100 meter, further progressing and further progressing. So in fact, this is a 3D distribution, and this is the east-west line. And if you see the north-south, I mean the dip is towards north, and very clearly dipping structure can be seen. And by putting the borehole data and this geophysical data, once we try, we can actually we could locate these mark different sandstone, shale, and the limestone, even granite. I mean the Amalani igneous suits are there, the spin color. So thanks a lot. I think I have to do some.
Thank you, Dr. Subhash Chandra, on a very interesting talk on integrated geophysics for deciphering subsurface structure, for various very good work on the paleochannel studies of Ganga Plain. So I'm afraid we don't have time for any questions. So, but I would like to encourage you all, because Dr. Chandra will be around, so you can just personally talk to him. And with this, we conclude this session. Thank you.
Thank you.
So with Dr. Subhash Chandra's enlightening presentation, we conclude the Day 2 technical session. On behalf of the organizing team, I sincerely thank all our distinguished speakers for their valuable insights and contributions to advancing geophysical methods and mineral exploration strategies.
Now it's time to felicitate our speakers for their enriching contributions. I invite our session chair, Dr. L.P. Singh, Deputy Director General, State Unit Telangana, Geological Survey of India, to kindly do the honors. May I now call upon Mr. G. Karunakar, Steiger Geoscience and Engineering, for his talk on advancing mineral exploration with cutting-edge geophysical surveys. Thank you, sir. Dr. Subhash Chandra, CSIR NGRI, for his insightful presentation on unlocking near-surface structure by integrated geophysics. Thank you, sir. Finally, I invite Sri Vijay Vishnupant Mughal sir, Additional Director General and HOD Western Region, GSI, to felicitate our session chair, Dr. L.P. Singh, sir.
Thank you so much, sir. We now move to a highly anticipated part of today's program, the expert panel discussion. Next-gen geophysics and India's role in global critical mineral security. This topic is of critical national and global importance. As the world shifts toward green technologies and clean energy, critical minerals like lithium, cobalt, rare earth elements, and graphite are vital for economic resilience and technological sovereignty. Our panel features leading experts from science, industry, government, and technology innovation. Without further ado, please join me in welcoming our moderator, Professor Alok Porwal, Institute Chair Professor, CSRE, IIT Bombay.
Key discussion points we will explore in this panel discussion, which includes how can advanced geophysics enable deeper, faster, and more sustainable mineral discoveries? What strategic role can India play in the global critical mineral supply chain? How do we align exploration innovation with policy, industry, and national priorities? And how can academia, government, and industry partnerships future-proof India's mineral security? Now let me introduce the panelists for this panel discussion. The first panelist is Mr. Sandeep Roy, DDG NMH2. Sir, if you kindly proceed to the stage, please. Please give a huge round of applause for. Our second panelist, Dr. Y. Satyanarayana, Director, Critical Mineral Trackers. So please come up on stage. our third panelist, Mr. Anirban Manna, Automyonics. The fourth panelist for today's panel discussion, Dr. S.N. Mahapatra, DDG State Unit, Andhra Pradesh. And our final panelist for today's visionary panel discussion, Dr. Santanu Bhattacharya, DDG State Unit, West Bengal. So kindly proceed to the center stage.
Yeah, good afternoon, everyone. First of all, I welcome the distinguished panelists for this discussion on critical metals. And I would encourage the audience to participate after the panelists have put forward their point of view, so we can have a very short, quick inputs from the audience as well. So, critical metals, they got basically two constraints before we call something critical. It's nothing geological, so it's about the criticality for the green technologies as well as of attaining the sustainable development goals. And the second is their criticality for the supply chain risk that's involved in that. We know recently China has stopped the exports of rare earth elements, and that has started to affect all the electrical vehicles. So they are important, and the definition of critical metals and critical minerals change with the country. For our country, nickel is a critical metal, but for Australia it may not be. So in this discussion, we are going to focus on the minerals that are critical globally, because we are talking about India's role in the global critical minerals security. So we would be probably talking more about rare earth elements, battery metals, lithium, which have got huge relevance for electrical vehicles. So we begin with Dr. Roy. In terms of geophysics, given the geological constraints and the diversity of environment in which we can get critical metals, how or what kind of geophysical tools are going to support critical metal exploration?
Thank you. Very interesting aspect to start with. As far as the critical global scenario is concerned, like there has been a lot of forums of late globally in which India is a partner. For example, we have got a Mineral Security Partnership Forum floated in 2022, and in 2023 India became a partner. 14 members are there, basically to address the supply chain, the vulnerability in the supply chain, and to assist each other right from exploration till production and stockpile as well. So here we, last 2 days, we are actually into the exploration part of it, wherein the role of geophysics, I'm coming to exactly to that point, becomes very vital. In a way, like I'm a geologist, but what I understand that these critical minerals, this list of critical mineral is dynamic. Today it is 24, tomorrow it will change. Again, if we become self-sufficient in something, the other mineral will come in inside this. But the key aspect, the key important minerals like the battery elements, these elements, 5 or 6, these are critical in green energy, the electrical vehicles, the solar. So almost UN and India, almost they have mapped this, and we probably know the exact quantum we'll be requiring and the projections thereafter. The interesting part is where to find them. Now, as a geologist or as a geoscience community, we know that these elements in the periodic table doesn't occur in isolation. So the key factor is knowing the association, the companion ability of these elements with some major elements, like copper has got some companion critical minerals associated with it. We have got a lead, zinc, they have got some critical mineral associated with it. We have got aluminum, we have got so on and so forth. The example goes on increasing. So the idea would rather be target these common stock mineral systems wherein we get some bunch of critical minerals. Now when we come into the mineral systems are much more tougher to decipher than easier said that this is a mineral system we understand. For example, years together we have not been able to resolve the Malanskan porphyry system. Even we still are having a debate. We have got 2-3 schools of thought. Oh, this is like that, this may be a porphyry system, this may not be a porphyry system. Herein comes the utility of geophysics. And herein comes the utility of sort of a deep surveys, some deep studies like you have got a magnetotelluric or a DSRS. Like DSRS before used to be thought about only in oil industries, but now this is becoming very important. I'll give one more example and pass it on to the panelists. Take for example the Deccan Trap, for example. Till now the Deccan Traps had not been a focus of exploration per se, but then there are mineral systems like the Norilsk of Siberia where you have got a nickel PTPD exploration. Now these explorations, this type of data throughout the world shows that if we get this type of deposits beneath the Deccan Trap, we need a huge contribution from the next generation of geophysics instrumentation, technology and the exploration. Remember, geophysics won't be able to go together. It has to go in hand in glove with geochemistry, geology, as well as geochemistry, the other aspects as well. I think with this, I give it to the other panelists.
Thank you very much for your views. Dr. Satyanarayan, you're from Critical Metal Trackers, so you are essentially doing the hands-on exploration. So what would be your suggestions about the tools and techniques for exploration of critical metals?
Good afternoon. The critical minerals, we know the importance of the critical minerals today because they are very scarcely available. And after China stopped exporting those things, we are unable to import many countries, not only India. So the importance of the critical minerals has come up. Because earlier they were available only very less abundance. We are not much bothered about those things because we are looking at very high percentage of minerals in the deposits and all. But today, even the very less percentage, even decimal ppm is also very important today. But present technologies like geophysics or geological investigations or geochemical, will they help us? Because we just look at differently. Because geological of geochemicals, you are seeing directly the samples and what the content of it. But geophysical, when it comes to a deep-seated, we will be having a problem in identifying those areas. Because being their availability is in less abundance, I can say there is no geophysical method or any method which is directly can identify the critical minerals because of their less abundance. So what is the solution then? We should see that because that is available as a secondary mineral or some associated mineral. That is the one thing. So you need to find the host rock or that is host rock only. That is the one, whether it is deep or shallow. So geophysical methods are very helpful. Particularly we know that even the recent technologies which are discussed for yesterday and today, they are very good in identifying the deep mineral sources and all deep deposits. So which I think combining all the geoscience like geochemical, geological information and many multi-parameter geophysical data can help us to identify and narrow down these resources in the host rock or somewhere. Then you confine to that areas and limit the resource, particular resource management and the cost cutting advantage. So using the AI technologies further, which is very helpful, we know that I don't have to say about what AI can do because with the big data, because AI, when it comes to AI, we talk about the data. Without data, there is no AI. So when you have multidimensional nonlinear parameters, then we have to use AI where we do not, the physics between these, to establish a relation between these various parameters. That's what AI is a prominent and promising technologies using the combined geoscience data. And that is, I think now the revolutionizing the mineral industry also in the coming few days But on the mineral sector, because it's a late edition, I can say, because of the experts from different disciplines have to come. It's not only the computer science, it's not only the artificial engineering, data scientists, geologists, geophysics, and geochemists, all together have to work together. It encourages sharing the knowledge and also the collaboration of the agencies, among the agencies. That's today's thing that can solve to some extent in finding the successfully critical minerals. And apart from that, we are also e-waste. It's e-waste from extraction of the critical minerals from e-waste, particularly lithium and all, batteries and some e-waste and all. That is as another parallelly going on. That's a very promising area. Of course, MT, we are also doing partnering with IITs and some other primary institutions in this regard. Thank you.
Yeah, thank you, Dr. Satyanarayan. Anirban, I'll get to you here. Given the wide range of and geological settings in which you find critical metals, you got nickel occurring in ultramafics, comatite-hosted nickel sulfides. On the other hand, you got lithium, which typically goes with highly evolved pegmatites. So on one hand, you got completely unevolved primitive magma and hosting nickel. On the other hand, you have lithium occurring in highly fractionated rocks. So what kind of geophysics do you think is going to help us identifying the whole suite of critical metals?
I like that we are starting with the fundamentals, figuring out what it takes to find these resources. But I think there are a bunch of things we could do to identify the geological structures that allow, that permit the existence of these resources. But I think the question that we have been asking at Atom Ionics is, how do we find things faster? How do we not just find things, but make sure that we're finding enough of these to satisfy the demands for these minerals? And AI has been a huge topic in the last 2 days, and I was having another conversation with someone yesterday, and they were asking about how exactly the AI is working in identifying some of these minerals. And I guess the pro and con of AI is that it's a black box. And it sort of reminded me of a conversation that we were having with one of the original members of OpenAI, and they were saying that we need to think about this from an unbiased perspective. We need to go in and train the AI model with all kinds of data sets and not worry about whether it's going to be useful in finding a specific type of mineral, because we introduce biases through these initial judgments. So let the AI figure out what are the environmental conditions that permit the existence of these minerals. It could be, perhaps temperature for whatever reason that we may not know, but the AI might find some level of correlation. So there's a lot of these things that are going on the AI side, but at the end of the day, it's also about fundamentally changing how you're collecting data, because a lot of people have been working on AI. They have tried it on existing data sets, but it's been really difficult to find new deposits through this method. And so that's where we realize that you have to also change the data that you're collecting, how you're collecting the data. And so it's going to be really a combination of the two that will allow you to identify or even build our understanding of what these models look like.
Thank you. I get your point, and I think it's a very interesting point that you made here. The constraint with all these AI methods, machine learning, is particularly the lack of training data, and we really don't get to see too much of training data when it comes to critical metals in particular, because we have only recently started to focus on critical metals. We don't have all that many of deposits known, but definitely AI can go a long way. Now shifting the gears a bit, I would like to go to Dr. Mahapatra here. And the question is that given the importance of these critical metals and the risk to the supply chains that we are seeing of late in the global geopolitical environment, how do we align our exploration, innovation, and how do we align our policies that are more conducive, more encouraging, invites more investment in critical metal exploration?
Good afternoon, all. I belong to an exploration agency, Geological Survey of India, and I am a geologist. From that angle, I would like to say that we know what are the critical minerals, commodities for India. After 2022, after that listing has been done that these are the minerals which are critical for India. So the first thing that we should know is that these critical commodities, they have an association. That is, commodities have some host associated with some host rocks, some environments, some structures. So we have to identify this, that you have already told in the previous part only, that some of the commodities are associated with granitic host, some are associated with the ultramafic host, some are with the mafic host. So similar things, and not only the entire rock is mineralized, but a certain part of it will be mineralized. So once we identify those kind of things, then you have to concentrate your all kind of exploration strategy to find out those commodities. So this is a part of this internal exploration strategy. But while doing that things, we also have to look into many of the dumps or the beach sand and all these areas where we have already explored some bulk commodity, but they are also associated with some critical commodities. So the dumps or the recycling of the dump areas as well as beach sands, these are also very important for us. We have to also just, government policy is now is that we are also trying to acquire some of the mine or leases abroad through Kabil agency. So ultimately the thing is that there are two-pronged strategy has been done. One is exploring within the country and also through acquisition. So both the strategies we are adopting, but we need to be very, very fast, and we should accelerate the process.
Yeah, thank you, Dr. You made really a good point. Particularly, the bigger source of critical metals is probably coming from secondary resources, recycled material, as well as batteries and other things which are recycled, and we again extract the metal out of it, but also from the clay-hosted secondary deposits which are found over carbonatites and these other rocks, as well as we have to look into non-conventional sources, for example, brines, and extract metals, battery metals from brines. Dr. Bhattacharya, coming to you finally, how do you envisage the academia, the industry, and the key governmental agencies, particularly Geological Survey of India? So how do you envisage that these three components, which are into exploration, what kind of synergy should develop between them so that we can optimize our exploration? In terms of the kind of resources that Geological Survey of India has, probably academia would not have, but the kind of expertise that academia has, probably Geological Survey of India can dig into that. So how do you envisage this synergy developing?
Good afternoon. See, critical minerals are those which are necessary for the development of the country. They are critical because in some way there's a demand is high, or the supply is less, or recycling potentiality is low. And as my earlier speakers told, that integration of geology and geophysics is the best way to explore it. Geology, because as Mahapatra told, some of the elements are associated with some particular lithology, so geology is very essential. And geophysics will help in determining the structure, deep structures like your airborne magnetics or ground magnetics and EM, MT. Radiometrics, of course, will be very helpful. Now, Government of India has recently published a list of 30 critical minerals. If you go through that list, out of the 30, 9 or 10 are associated. They are minor elements which can be recovered only through beneficiation. Some of the industries, they are experts in beneficiation. GSI doesn't have that expertise. So if we have to develop and go in this way, then there should be a synergy between academic exploration agencies as well as the institutions which have this expertise. And academics can definitely help, institutions can help in giving the analysis part. Exploration agencies will do the exploration, and other research institutions, they can help in developing the flow chart and all. I'll give a small example of State Unit West Bengal. There in one of our deposits, we got a very good rare earths are there, but they're all associated with allanite, apatite. And if we see some of the important deposits in our country, they are associated with silicates. It is very easy to beneficiate from phosphates, but it is really difficult to beneficiate from the silicates. So if such methodology can be deduced, then the economy will definitely increase. So there should be a complete synergy between these three.
Yeah.
So.
Thank you, Dr. Bhattacharya. In fact, you made a very good point, and we really don't have the time to discuss that, but I think extraction is a bigger problem than exploration when it comes to critical metals, and a good amount of focus, and I think IBM got good expertise in this, and maybe the institutes like ISM or IIT Bombay have got good departments. So a lot of work needs to be done in that domain, extraction domain. So what comes out is that we really need to look into the geology of the deposits to begin with, where they are occurring, how they are occurring, given the large variety of environments in which they can be found. They've got different petrophysical properties, so we would need different kinds of geophysical surveys or geophysical techniques to explore them. So it cannot be just one size fits all kind of exploration for critical metals. And of course, the government, the critical metals are top priority for Government of India right now. There's a lot of funding available for exploration. I would quickly go to the audience and maybe one or two suggestions if we can get from the audience, it would be fantastic. So anyone who would like to comment on the discussion that we're having today? Yeah, please.
I'm A.C. Dinesh from Geomarine Solutions. I would like to add 2 points here. One is, Dr. Mahabatra has rightly pointed out, he has told one sentence, granite hosted and ultramafic hosted. Then Dr. Satyanarayana and Mr. Anir Barwe talked about AI. My personal feeling is that without the correct, real, clear knowledge on mineral system science, the AI will be a failure. Because without applying that knowledge, clear knowledge, what Mahabatra was talking about, AI can be attempted, many people, but without this knowledge, it will be a failure. Now GSI also coming out with a big program of AI. So certainly GSI geologists have that good knowledge about the mineral system science. That is one point. So we should put a caution when we apply AI. Number two, regarding this critical minerals, we should seriously think about why we are lagging behind in beneficiation and extraction. Why? You see, last 10 years, GSI augmented their exploration programs many-fold. MECL has come, GMDC, NMDC, many NPAs, notified agencies from 2018-19. That is a big initiative by Ministry of Mines. About 30 odd, more than 30 NPAs are there now. Now if you look at the exploration programs, especially for critical minerals, it is so many, several, maybe about 500 or more than that one. So good augmentation in exploration, but why we are lagging behind? That is a question I am asking the panel. Where we are lacking? Where we lost? Without a beneficent extraction, when we do exploration, we are not going to achieve the goal. The critical mineral mission goal, we cannot achieve within 6 years. Thank you.
Yeah, I absolutely agree with that. Lithium will have lepidolite hosted lithium rich deposits, but not possible to extract it out. So should we be looking for spodumene hosted lithium, or should we develop technology for extracting lithium economically? And that's where China is doing so well. So China is not only about exploration. They are much better, much far ahead in beneficiation and extraction of metal, and that's why they are leading globally. They've got the monopoly over critical metals. Any other suggestion from the audience? Yes, please.
Yes, sir. I am Naresh Agarwal from Pan India Consultant Private Limited. So I would see that geochemistry has a larger role to play in the critical minerals because the property of the critical minerals and the normal minerals are the same in terms of the geophysical. So what we are doing in the geophysical survey, what we are already doing, so they have the same physical parameters, same physical properties, the methods, basic methods what we are applying, the gravity, magnetic, and electric properties are the same. So we don't see any like new properties in the critical minerals which can help us to develop new technique in the geophysical domain. But the geochemistry has a larger play. We have a lot of core samples available with the GSI, with all the exploration agencies. So if we can properly analyze those samples, the core samples, whether with the core scanning, physical analysis, and then we can create a database which can help in, I think,
yeah, I think that's a very good suggestion, and particularly re-looking at the deposits that we overlooked initially, because no one was even thinking about the present. Yeah, it's the last one because we are running short of time. So yeah, please, last one.
Thank you, sir. I'm Avik from Geological Survey of India. It's not a question, it's not a suggestion, but a question to Dr. Parwal, Satyanarayan sir, and the panelists. Sir, where we are applying for AIML, where we have a supervised classification, where we have already a known deposits in that area. But many of our greenfield terrain, as we were speaking about the Deccan traps. So as of now, there are no known deposits there. But is there a possibility that we draw analogs from examples from global context, as you are telling the Norilsk or the Siberian trap, and that data, since we don't have deposit, but the nature of the lithology or structure or the time of formation of those rocks in that area, can it be put into a form of a unsupervised or a semi-supervised classification so that we can track the critical mineral possibilities there? For example, we are not getting anything in Deccan trap as such, but when we are targeting the laterites which are covering the Deccan traps, we are getting some indications of critical minerals enrichment in them. So that sort of modeling, whether there is a possibility.
Yeah, I take your point, and I think it's a very valid point. And given the lack of known deposits, we don't have all that many critical metal deposits known. So absolutely, it's probably we have to focus more on the unsupervised methods when it comes to artificial intelligence. And there are very good algorithms, in fact, fantastic algorithms for, particularly if we use deep learning for clustering and using non-linear methods. So getting the global analogs and developing a kind of database which has got a global perspective and develop a training data and maybe start your clustering analysis from there and see how they are able to predict deposits there, and then try and apply the same techniques in green fields. So essentially, if you lack the training data, then unsupervised is the way to go. And in geology, in fact, because we are not able to see the features visually, in fact, no geophysicist by looking at a magnetic image can tell you that there's a deposit there. No, it's a kind of an interpretation that goes into it. So when things are not obvious to eyes, then obviously we need to look at the same aspect from different angles, so multiple data sets, and then cluster them and then look at an integrated view. So absolutely, that's probably the way to go. So yeah, thank you, good suggestion.
Thank you, sir.
I would really have to wind up now, probably running short of time. But what comes out of this discussion is that there's not going to be one size fits all for all critical metals, given the wide range of metals that are there, is starting from nickel to lithium to rare earth elements, and then you've got non-metals like graphite, which are very critical. So for all these, we've got different geological settings, so we probably have to evolve a commodity-specific technique for exploration. And what also comes out is that we probably need to invest a lot more in extraction of metals, the beneficiation, rather than exploration is going to go on, and Geological Survey of India is doing a fantastic job there, and there's a lot of private participation. So that's going to work very well. But we need to focus a lot more on extraction part. So thank you very much. I thank all the panelists once again and the audience for very active participation. Thank you.
That was an engaging and thought-provoking panel discussion. Our sincere thanks to all the esteemed panelists for sharing their strategic insights and perspectives on the role of next-generation geophysics in securing critical mineral resources, a subject that will undoubtedly shape India's position in the global resource landscape. And with this, we are concluding the technical session of Next Gen Geophysics 2025 conference, organized by Geological Survey of India Training Institute, Hyderabad. And in last couple of days, we exchanged valuable ideas in the domain of cutting-edge geophysical technologies. Please give a huge round of applause once again for all the speakers and the participants who made this conference a huge success. Now we'll proceed to the valedictory session.
So let me hand over the stage to my colleagues, Mr. Rahul Dhiman and Ms. Annie Delia Nelson, who will be your host for the final segment of the conference. Thank you.
Thank you.
Thank you so much, Suman and Abhijit. Good evening, ladies and gentlemen. It is time to formally bring down the curtain on what has been a truly enriching and intellectually stimulating event.
Yes. Welcome to the valedictory session of Next Gen Geophysics 2025, Unlocking Earth's Hidden Treasures, a two-day transformative journey of learning, collaboration, and innovation.
This valedictory session provides us an opportunity to reflect on the key insights, acknowledge contributions, and chart a course forward in the evolving landscape of geophysics.
To commence these proceedings, I have the privilege of inviting the convener of this conference, Dr. S. Ravi, Deputy Director General, and Head Mission 5, Geological Survey of India Training Institute, to kindly come forward and take his place on the dais.
A gracious welcome to you, sir. We are also honored to welcome Shri S.D. Patbhaje, Additional Director General and Head of Department, Geological Survey of India Southern Region. Sir, may we request you to kindly join us on the stage and take your seat on the dais.
We are really thankful for your presence today, sir. Next, we are deeply honored by the presence of our Chief Patron, Sri Asit Saha, Deputy Director General, Geological Survey of India, a visionary leader whose unwavering guidance continues to shape the geoscientific landscape of our country.
Sir, may we request you to kindly take your place on the dais. It is a privilege to have your leadership and presence with us today. Going forward, may I now invite Dr. Pradeep Singh, Deputy Director General and National Mission Head 1A, to please present a comprehensive summary of the conference deliberations, highlighting key outcomes, insights, and the way forward. Please give him a huge round of applause and welcome him.
Geophysics, new techniques, next generation geophysics. It was really an eye-opener for me because I was in the ministry as director for 2 years and then director technical for 5 years and attending number of conferences in India during this period. So this is really because I have been keenly watching the progress of mineral exploration for last 7 years. So this is one of the conference where the geophysical community of the country, including GSI, they have come to know about what is going on in the outside India and what techniques are being applied. So I think this will give a very important lesson to all of us. And the takeaway would be that Geological Survey of India will start employing some of these technologies, techniques, new techniques in mineral exploration, geophysical techniques, and we have now a good ecosystem in India of the private exploration agencies. So private exploration agencies are submitting lot of projects through NMET funding. And we have been seeing that these private exploration agencies also, whatever projects they are submitting, it is all conventional exploration and conventional geophysics. Now with this changing time, so these new techniques and new concepts will also be adopted by the private sector in India. So number of speakers have thrown light about different techniques, and some of the sensors like this next generation Condor ALG, it is under development, and maybe within 4 or 5 years we will get better this geophysical instruments. And then this session by Aniram Mana, it was really enlightening, and the system, the innovative gravimeter sensors powered by cold atom interferometry they are using, and they have been with these new techniques, they have been able to actually reduce this uncertainty in the selection of the boreholes, because see, the borehole actually the only 10% or 20% success rate is there. But with after application of these new techniques, this the success rate will increase maybe 70-80%. Then the carbon emission will also come down, and the pace of discovery in the country is supposed to increase, because we are on the verge of cusp of the Geological Survey of India, the whatever explorations they are doing. See, our orientation was for conventional type of exploration only, and since this thinking of and focus towards critical mineral has changed in last 5 to 6 years, so that focus has also now shifted in our country, and GSI has started focusing more on these critical minerals, deep-seated minerals, and we are taking almost 70%, 70 to 80% of the items, which are basically either of critical minerals or having some critical mineral bias. And the private exploration agencies also, through NMET, we are only encouraging the companies to come up with critical minerals and deep-seated minerals items. So now this we see Geological Survey of India and as well as private exploration agencies, we are aware that we are on the brink of several good discoveries. So maybe within 1 or 2 years, GSI will announce very good discoveries in India based on the exploration programs they are carrying out, and we are getting good feedback from the private sector also. Based on the recently last 2 years, the exploration they have carried out through NMET, some very fantastic results have come up, and some for critical minerals, rare earth minerals, some new districts, almost new districts are going to come up in several states. So these techniques will be really helpful to us now for accelerating our mineral exploration program. And with a lot of these new techniques like FTG and this gravimeter, this cold atom interferometry, innovative gravimeters, etc. These applications, this will lead us to the new exploration, new kinds of exploration. So I hope that see from National Mineral Exploration Trust now, because we are in the process of evolving the new SOC for that. So I think because in geophysics, almost we need to incorporate all these components in our SOC, and because every mineral exploration project should have some financials quantification. So we will now adopt these all these whatever new techniques we have come to know through this conference in our SOC also, NMET SOC also. And with this I conclude, because it was a very satisfying and very provocative, thought-provocative session, workshop. Thank you, everyone.
Thank you, sir. Thank you, sir, for clearly and effectively summarizing the key points and highlights of this conference. Ladies and gentlemen, we now take this opportunity to express our sincere appreciation to the various stakeholders who contributed significantly to the success of this event. May I request the dignitaries seated on the dais to please come forward for the felicitation ceremony of our sponsors and exhibitors.
We begin by recognizing our sponsors who also participated as exhibitors. May I request Shri Asis Saha, Director General, Geological Survey of India, to kindly present mementos and certificates of appreciation to our sponsors cum exhibitors. We request the representatives of each firm to kindly come forward as their names are announced to receive the tokens of appreciation from our chief patron. So we'll start with Critical Mineral Trackers, Platinum sponsor, cum exhibitor. So please. critical mineral trackers, platinum sponsors, come exhibitor. Next, Mining Tech Consultancy Services, MTCS, platinum sponsor, come exhibitor. Data Code Geoscience Private Limited, platinum sponsor, come exhibitor. Mineral Exploration Consultancy Limited, MECL, gold sponsor, come exhibitor. Please give our sponsor a huge round of applause because it is for their efforts and contributions that this event has been made possible. Altera Solutions LLP, gold sponsors come exhibitors. The representative of Altera Solution is currently not with us. So we will move ahead with Geomarine Solutions Private Limited, gold sponsor, come exhibitor. Please, representatives of Geomarine Solutions. The representatives of Geomarine Solutions Private Limited. Hind Metal Exploration Services Private Limited, SZL, gold sponsor, come exhibitor. Hind Metal Exploration Services Private Limited, SZL. Do you have the representatives of SZL? No? Okay. Bell Geospace and Summit Spectrum EIT Private Limited. They are gold sponsors, come exhibitors. The next one is Spry Technocon Private Limited, silver sponsor, come exhibitor. Spry Technocon. Please, sir, please come to the stage. GeoExpo Private Limited, silver sponsor, come exhibitor. Please give him a huge round of applause.
Next, we acknowledge our sponsors whose generous support enabled the seamless execution of this conference. For this, may I request now I request Dr. S. Ravi, Deputy Director General and Head Mission 5, Geological Survey of India Training Institute, to please present token of appreciation to our sponsors of this event. So first, let me call upon United Exploration India Private Limited, the silver sponsors, please come onto the stage, followed by Maheshwari Mining Private Limited. Maheshwari Mining Private Limited, silver sponsors of this event, please come forward. Thank you.
Finally, we recognize our exhibitors whose engaging and informative displays significantly enhance the delegate experience. For this, may I request Sri S.D. Patbhaji, Additional Director General and Head of Department Geological Survey of India Southern Region, to please present token of appreciation to the exhibitors of this event. We will start with Steiger Geosciences and Engineering Private Limited. Please, the representatives from Steiger Geosciences and Engineering Private Limited. Followed by Shijay Projects India Private Limited. Shijay Projects India Private Limited. National Institute of Rock Mechanics, NIRM. NIRM. All Geo Solutions. Please give our sponsors a huge round of applause, as well as our exhibitors. All Geo Solutions. Integrated Geo Instruments and Services Private Limited. All Geo Solutions. Integrated Geo Instruments and Services Private Limited. Please, sir. AML Limited. Representatives from AML Limited. Wave Geoservices Private Limited. Wave Geoservices Private Limited. Pan India Consultants Private Limited and Sanders Geophysics India Limited. Pan India Consultants Private Limited and Sanders Geophysics India Private Limited. Please mind your step. Last but not the least, Myonics India Private Limited. Myonics India Private Limited.
Thank you all. So please be seated. Thank you all. Your presence added immense value to this event, and we thank you for being a vital part of this successful conference and look forward for further associations. So moving further, it's now distinct honor to invite Sri Asit Saha, the Director General of Geological Survey of India, to deliver the valedictory address. Please.
Under his visionary leadership, the Geological Survey of India continues to make significant strides in advancing geoscientific exploration and knowledge dissemination. Please, sir, give him a huge round of applause, people, and welcome him.
Hey guys, good evening, good afternoon, and eventful 2 days. And I guess I have never seen a valedictory session this full. Good. Maybe that's why the organizers kept these prizes for you. Anyway, so a lot has been spoken. And if I go back to my inaugural address, then you might remember that I said that we need to know in great detail about the subsurface. And time and again, all the speakers, they have reiterated that thing, that we need to know the subsurface in as much detail as possible, and that subsurface is now not limited to the 50 meters down below, 100 meters down below, but it goes to kilometers. And the technologies which we have witnessed gives us those opportunity to chart that path. Be it mineral exploration, natural hazards, understanding the earth, for example, the systems which is occurring on the earth. We as geoscientists, we are sort of, you can say, worshippers of the earth, worshippers of the processes which act on the earth. We try to understand them. We have been doing them for years together. And we can say that yes, we understand so much about the surface processes, but we are still at large, we are at dark about how exactly things happen down below. There are speculations, there are theories, there are hypotheses, but confirmation of those theories, we need geophysics. I think that has been stamped clearly, unequivocally, that we need geophysics to go ahead in a scenario where there are umpteen challenges before us. The biggest one of them would be clean energy transition. And it is that clean energy transition goal which is actually driving every other thing at this moment for all geological surveys all over the world. When we are talking of critical minerals, it is actually keeping that in view. And when we are
talking of AI. AI has, two panel discussions we had, and the panel discussions had topics, next-gen geophysics and this, but ultimately all panel discussions centered around AI, how to use AI. Using AI in geosciences is a bigger challenge that anybody can understand. Why so? I mean, AI has been immensely successful in using transactional data like retail, commerce, e-commerce, in telecommunications and all those things, where probably the variables are easier to understand and manage. But when we are dealing with complex processes in geoscience, in nature, per se, I mean, it's a long way to go for us. It's a long, long way to go before saying, well, this is it. We cannot say this at this moment. We are not in a position. And that was evident from the questions which were being asked, the discussions which we had. So whatever comes out of these things is that there are immense scope for innovation. There are a lot of challenges, and all these challenges are actually opportunities for us geoscientists, for us thinkers, for us innovators. There is a lot of scope for research, a lot of scope for innovation. And working in silos will not help us at all. We have to come together. That was the basic philosophy of this conference. If you have noticed one very simple thing, but very significant thing about this conference is that there was no presentation from GSI. We didn't want to tell you what we were doing. You must be knowing by the time what we are doing. We wanted to know what others are doing. And we wanted to let you know also what others are doing. And we want to walk the path together. I am extremely excited after seeing some of the presentations. I unfortunately missed today's morning lectures, and I rue the fact, but whatever I have seen yesterday and in the afternoon session, I'm extremely excited. For example, I'm very excited. I talked with Anirban. I am very excited to see this drone-based gravity survey. We have started doing drone-based magnetic survey, but I'm looking forward to the day when I'll be able to do this drone-based gravity survey, when I may not have to go to DGC and other permitting agencies. My NAGMP program is facing the biggest challenge from this permission scenario. All my timelines are going haywire. I don't want that. I want technologies which are portable and effective and less time consuming. So I guess if I have this technology with me today, doing gravity survey using drones, I would jump at it. Considering the topography, the terrain, the population density of our country, I need technologies where I can do, that non-invasive survey sort of things. I don't want explosives to do seismic surveys. I can't afford that. I may be running door after door, trying to get permission from this authority and that authority. So I need some technology, which will help me do that without disturbing my neighbors, my fellow people. Because I have to do that. I have to find new deposits. I cannot say that I can sleep tight today. I have a lot of challenges. So this conference has been, as Dr. Pradeep Singh has said, an eye-opener for him, an eye-opener for us, and probably for some of you too. And I can see my fresh new batch of scientists who will be starting their journey in GSI sitting at the back. I guess it has been an exhilarating experience for them too, because it is you to whom I am looking forward, because you are going to adopt these technologies in the near future. It's not that they are, most of them are not probably intensively and aggressively associated, or available in India today. Maybe it will take some more time, but this is the future, man. You have to study these things, and let us not keep it restricted only to geophysicists. Let us think ourselves as geoscientists and work together. I think I have made my point. There are a lot of outcomes, a lot of takeaways from this conference, and we will take this forward. We will take this forward in many different ways. We will follow up with many of you who has presented here. We'll try to do some pilot projects with you. We'll try to find out the right application for our problems. We have our problem statements ready. We'll see whether your technology fits the bill. And we are a government agency. We do not have that, flexibility to just ask you, come do this job. We cannot do that. We have to follow certain rules and regulations. And I guess you are also very much aware of those things. But even if we are not able to, employ you ourselves, we will promote you, because there are funding agencies, there are other companies who are having that flexibility which we lack. We would like to promote these new age technologies. That would be beneficial. It would be a symbiotic relation for all of us. So having said that, I rest my case. Thank you all. Thank you for joining. And before I end, I would, they are calling me as the chief patron of this conference. As the chief patron, it's my duty to actually congratulate my team who has made this conference possible. So a big hand for all of them, all the organizers. Thank you.
Thank you, sir. Thank you for your inspiring words, and also for gracing this event with your presence and leadership. Thank you so much. So moving further, at this moment, I would request our DGGSI Sri Asit Saha to please honor our Additional Director General and Head of the Department, Geological Survey of India Southern Region, Sri S.D. Padwaje sir, with a token of gratitude.
Okay, this is something which I would also like to say. Mr. Padwaje, after an illustrious career in GSI, he is going to put down his papers this month. So, one round of applause for him too. It should continue for a minute.
Thank you, sir.
Please give him a huge round of applause. Now, as a token of our deep gratitude for his unwavering support and distinguished presence at this international conference, I now request Dr. S. Ravi, Deputy Director General and Head Mission 5, Geological Survey of India Training Institute, to kindly felicitate Sri Asit Saha, Director General, Geological Survey of India, with a token of gratitude.
His visionary leadership, steadfast commitment to scientific advancement, and encouragement of innovative geoscientific initiatives have played a key role in shaping the direction of this conference and the broader mission of the Geological Survey of India. Thank you so much, sir, for being with us on this occasion.
Now, to formally express our gratitude to all who made this conference a grand success, may I invite Shri A.B. Ekka, Director and Head of Office, Geological Survey of India Training Institute, to deliver the vote of thanks. Please, sir.
Thank you, Rahul and Annie. It is going to be the down, but I think it's a new beginning. So with this, I would like to formally express my personal and institutional word of thanks. A very good evening to all, ladies and gentlemen, scientists and respected dignitaries. We have reached towards the end of this two-day brainstorming and highly sought-after conference on Next Gen Geoscience 2025, Unlocking Earth's Hidden Treasure. Before we say goodbye, it's a time to acknowledge the contribution and immense effort put by all who have been part of these big events. So let's have a big round of applause of all. First and foremost, I would like to have my deepest gratitude to the Secretary of Mines, who is leading the entire ministry in the path of renewal when GSI completes 175 years in the history. I like to acknowledge the spirit and very deep interest to Sri G. Kishan Reddy, Honorable Union Minister of Coal and Mines, for his valuable time and inspiring speech on the day of inauguration, and who had inaugurated this event 2 days back. With this his kickstart, this event is about to complete successfully. I acknowledge and express my sincere gratitude to Sri Itala Rajendra, Member of Parliament of this area in which we are hosting this event, for his august presence and his remarkable event. I would like to give my deepest gratitude and thank to Sri Asit Saha, the Director General of GSI, who has brought this vision and scope to organize the first ever conference in geophysics in the history of GSI, which is today being completed. It is definitely a step to the new generation in which geology and geoscience join together and form a geosciences. I would like to thank the entire committee for the advisory committee who have been the member, and they have given valuable guidance and insight to conduct this event from the inception of its event. I would like to thank all the additional director generals and head of the departments of different regions who have been here physically present to contribute to the development of the science and bringing this energy and mind to the new generation. I would really thank to all. Thank you all, sir. I would like to thank Dr. S. Ravi, the convener of this two-day mega event, DDG and Head Mission 5, who is here spearheading Geological Survey of India Training Institute under Mission 5, and it is leading a team of dedicated faculty and all the directors and officers and the staff. And under his leadership, today we are seeing this event is being conducted at such a mega scale. Sir, I would really like to thank and congratulate you for this. It is my sincere thanks and gratitude to all the head of the institutions who have been present here on the day of inauguration. Sri Dheeraj Pandey, Director AMD, Dr. Prakash Kumar, Director NGRI, Professor Shalivan, Director Indian Institute of Petroleum and Energy. And I give my gratitude and thanks to all the session chairs chaired by Professor Alok Porwal, Professor C. Chakravarti, Sri D.V. Ganveer, Additional Director General and Head, GSI Central Region, Dr. L.P. Singh, Deputy Director General, State Unit, Telangana. The core of this entire 2 days big conference is focused upon all the scientific papers and the research work which have been presented online and physically standing at this place where I'm standing right now. I really thank, and it should be a great thank and applaud to all who have shared their knowledge and experience with us to take us to the new journey in which we go deep down and down and explore new resources from the earth and unearth them. I thank all of them who have been tirelessly worked hard and given their contribution in the development of the science. I also thank the moderators for the panel discussion who have chaired it so that we are focused together and understand the subject which has been discussed and presented among us. All the participants who have joined online as well as offline, they have traveled from their location and come here. Unfortunately, we could not accommodate within this arena. We believe that it should be double of the size. But those who have participated, it is really a future for them. And I think that this conference brings more enlightenment to them and also a new journey that they begin from the stepping ahead towards. All the stakeholders who have been part of this event, I really thank them, and I like to give them huge round of applause. Please have a huge round of applause for them. The event partner of this event, Steiger Geoscience, I think you have already applauded. Once again, it is for them. That has given us idea and understanding, and they have led us to conduct this entire program for last 2 days. Huge round of applause to all the sponsors under platinum, gold, and silver category, as well as all the exhibitors who have displayed their efficiency, instruments, their works, and their contribution to the industry, academics, and to the science. A sincere appreciation and applaud for all the team under which this entire event was organized, the entire organizing committee and various subcommittees on finance, technical, exhibition, reception and stage, decoration and hall management, refreshment and food, accommodation, transport, media and publication. Each member has tirelessly worked for more than a month to make this event a remarkable one and prove that they are efficient and they can deliver the best. A huge round of applause for them. All the staff and officers of the administrative team of Geological Survey of India Training Institute who have worked hard day and night, and they have given their best contribution. And I would like to thank all the outsourced staff for their day and night work and their continuous hard work for running this office and maintaining the campus in the way what we are seeing today. That is really pleasant. I believe the people who have stayed here have really liked it. We are working hard to make it pleasant and more better for you. And we thank IICT and NGRI for providing accommodation facility to our delegates and dignitaries who have been accommodated. I believe that they have really enjoyed and they have been comfortable for last 2 days. I thank trainee officers of 40th OCG who have been here and they have participated being as a volunteer. They have sung beautiful songs when the day was under cultural event. I think we enjoyed apart from science, and also they have contributed a lot, so we thank them with our core of my heart. And on behalf of the entire organizing committee and on my personal behalf, we express our deep gratitude to each and everyone who has directly or indirectly contributed to the successful completion of this mega event. Thank you all.
Thank you, sir. Thank you so much. So with that, we draw the curtains on our next Gen Geophysics 2025. We extend our heartfelt thanks to FVG delegates, speakers, partner, and organizer who contributed to the success of this global geoscientific dialogue.
Thank you once again for your presence, participation, and enthusiasm. Wishing you all continued success and safe travels. A small arrangement has been made, tea and refreshment you can have outside. I would request, I would request all the members of organizing committee to please get onto the stage for a group photograph. All the members of the organizing committee, please come forward to the stage for a group photograph. all the volunteers,